You know that feeling when you're playing a video game and you realize the NPC is just following a script? They walk the same path every day. They say the same thing. They exist only in relation to you, the player. What if I told you that you might be that NPC? Not in some paranoid tinfoil hat way, but in a way that's actually backed by legitimate physicists, computer scientists, and philosophers who take this question seriously. And here's the weird part: we might actually be able to test whether we live in a simulation. We might even have already found the evidence. This isn't science fiction anymore. This is science. But before we dive into the mind-bending physics, I want to take you back to a moment that changed how I think about reality itself. It was 3 a.m. I was sitting in my dorm room, staring at my computer screen, and I realized something that sounds stupid when you say it out loud, but felt profound in that moment. Everything I know about the world comes through my senses, which are just biological sensors feeding information to my brain. And my brain is just processing electrical signals. So how do I know those signals are actually connected to anything real? I could be a brain in a vat. I could be dreaming. I could be in a simulation. And suddenly, the universe felt less solid. It felt more like a stage. And that's where this story really begins. Not with equations or fancy tech, but with the ancient problem of how we know anything at all. But here's what's going to shift your perspective completely. In the last few decades, this ancient philosophical question has collided with quantum mechanics, computer science, and cosmology in ways that make the simulation hypothesis feel less like philosophy and more like testable science. And that's what we're exploring today. Let me start with the weirdest part of quantum mechanics, because understanding this is the key to everything that follows. You've probably heard that at the quantum level, reality behaves strangely. Particles can be in two places at once. Things don't have definite properties until you look at them. Physicists call this superposition and wave function collapse, but what it really means is this: the universe doesn't seem to have a fixed, objective reality waiting for us to discover it. Instead, reality seems to depend on observation. It's almost like the universe is lazy. It doesn't bother calculating all the details of what a particle is doing until something checks. And the moment you check, the moment you make a measurement, reality snaps into one definite state. This is called the measurement problem, and it's been bothering physicists for over a century. In 1935, Erwin Schrödinger, brilliant guy, total curmudgeon, came up with a thought experiment to show how absurd this idea seemed at the macroscopic level. He imagined a cat in a sealed box with a quantum particle. If the particle decays, which it might do or might not, it triggers a mechanism that kills the cat. So according to quantum mechanics, the cat should be in a superposition, both alive and dead, until someone opens the box and looks. The whole point of Schrödinger's cat was to say, "This is ridiculous. A cat can't be both alive and dead." But here's the thing. We've done countless experiments at the quantum level, and the math that says particles can be in superposition is absolutely correct. The weirdness isn't a bug. It's a feature of reality. Now imagine you're a programmer. You're designing a video game universe. You've got processing power constraints. You can't render the entire infinite world in perfect detail at all times. So you do what game developers actually do. You only render what the player is looking at. Everything outside the player's view is simplified, stored as data, not actively calculated. And the moment the player looks at something, You render it in full detail. From the inside, from the perspective of someone living in that game, it would feel exactly like quantum mechanics. Things wouldn't have definite properties until they were observed. You'd see superposition. You'd see wave function collapse. You'd think reality was fundamentally probabilistic. This is one of the first hints that simulation hypothesis isn't just philosophical, it's predictive. It makes testable predictions about how the universe should behave, and it does. But let's get deeper into why anyone takes this seriously in the first place. It starts with a guy named Nick Bostrom, a philosopher at Oxford. In 2003, he published a paper that basically said, if it's possible for a civilization to simulate a universe with conscious beings in it, and if that civilization decides to run many such simulations, then statistically speaking, we're probably living in one of those simulations rather than in the original base reality. Here's his argument in the simplest form. Take a hypothesis. Call it the ancestor simulation hypothesis. Imagine humanity survives long enough to develop the technology to simulate entire universes, not just some pixels on a screen. I mean full, detailed simulations where simulated beings develop consciousness and agency and have no idea they're being simulated. Once we have that technology, would we use it? Probably. Researchers would run simulations of how history could have gone differently. Hobbyists would run ancestor simulations, recreations of their own past. There might be millions of such simulations running, and Bostrom shows mathematically that if this is true, then the probability that we're in one of the original, non-simulated universes becomes vanishingly small, like less than 1% small. It's called the simulation argument, and what's beautiful about it is that it's not claiming we definitely live in a simulation. It's saying one of three things has to be true. Advanced civilizations never develop the capability to run full universe simulations, or they develop the capability but choose never to use it. Or we're almost certainly living in a simulation. One of those has to be true. There's no way around it. And when you think about it, option 3 suddenly seems less crazy. Because why would an advanced civilization with the power to simulate universes not do it? The scientific value alone would be insane. You could test any hypothesis about how civilizations develop, how the universe could have evolved differently, what the conditions for life really are. This is where things get interesting because it's no longer just thought experiment. It's starting to look like a genuine possibility that deserves serious investigation. Now, you might be thinking, okay, sure, maybe we live in a simulation, but how would we ever know? How could we test something like that? This is where it gets genuinely cool, and it's something that keeps me up at night. A few years ago, physicist James Gates was studying string theory. This is the theory that attempts to unite quantum mechanics with gravity, the two biggest frameworks in physics that don't play nicely together. He was looking at these mathematical structures called error-correcting codes. These are codes that computer scientists use to protect data from corruption. You send a message through a noisy channel, and the code lets you recover the original message, even if some of it gets garbled along the way. NASA uses error-correcting codes for space probes. Your hard drive uses them. They're everywhere in computing. Here's what Gates found. The same exact error-correcting codes he was studying in string theory, the fundamental equations describing reality, appear in the structures of space-time itself. Now, that could be a coincidence. It could be a deep mathematical fact about how information works, but it could also be something else. It could be that reality uses error-correcting codes because it's, well, computationally rendered. because it needs to handle information corruption the way any complex system does. Gates himself said it. This might be the most profound thing I've done. And remember, this is a guy who spent his life studying the deepest equations of reality. But there's more, deeper. In recent years, physicists have found something wild. The universe has a maximum information density. You can't pack more information into a region of space than what's called the holographic bound allows. This limit is incredibly restrictive. It says that all the information in the universe might be encoded on a two-dimensional surface, like a cosmic hologram, rather than being three-dimensional like we experience. The physicist Juan Maldacena actually proved mathematically that this is possible, that a lower dimensional universe can contain all the information of a higher dimensional one. This is the ADS/CFT correspondence, and it's one of the most important discoveries in theoretical physics in the last 20 years. Why does this matter? Because if the universe has a limited information density, if all the information in 3 dimensions can be encoded in 2 dimensions, then the universe is fundamentally computational. It's not that the universe is like a computer, it's that the universe is information. And information is something that can be computed, stored, manipulated. It's something that can be rendered. You're starting to see the picture. The deeper we look at the fundamental structure of reality, the more it looks like code, like information, like something that's being computed rather than existing in some absolute pre-given way. Let me tell you about my own encounter with this weirdness, because it's not just abstract. I was taking a quantum mechanics class, and our professor set up this experiment. It's called the double slit experiment, and it's been fundamental to quantum mechanics since the 1920s. Here's how it works. You take a light source, you shoot light at 2 slits. Behind the slits is a screen. If light behaves like particles, it should go through one slit or the other, and you'd see 2 bright spots on the screen. Simple, but light doesn't do that. When you're not watching, when you're not measuring which slit the light goes through, it acts like a wave. It goes through both slits at once, interferes with itself, and creates an interference pattern on the screen, multiple bright and dark stripes. But here's the disturbing part. The moment you set up a detector to figure out which slit the light actually goes through, the light changes its behavior. It stops acting like a wave. It starts acting like a particle. It goes through one slit or the other. The interference pattern disappears. Reality literally changes based on whether you're looking. We did this experiment in class. We set up the apparatus, ran it without a detector, saw the interference pattern. Then we added a detector. The pattern disappeared. Then we removed the detector. The pattern came back every single time, like the universe was watching us watching it. And I remember asking my professor, I'll never forget this moment, so the universe doesn't have a definite state until we look at it. And he said, yeah, that's the measurement problem. Nobody knows what it means. Nobody knows what it means. The smartest physicists on Earth have studied this for a century and still don't know what it means. That's not a bug in science. That's a genuine mystery at the heart of reality. But if you're in a simulation, it suddenly makes perfect sense. You don't have a definite state until you're being rendered. The computer isn't bothering to calculate every detail everywhere at all times. It's probabilistic until someone observes it. It's superposition until measurement collapses the wave function. It's exactly how you'd expect a computationally rendered universe to behave. Now let's talk about something even stranger, the fine-tuning problem. The universe has about 24 fundamental constants, numbers that determine how the universe behaves: the strength of gravity, the strength of the electromagnetic force, the mass of the electron. These aren't things we understand from deeper principles. They're just numbers. They're set. And if you change them even slightly, the universe becomes impossible for life. Take gravity. Make gravity 1% stronger, and stars burn out too fast. Stars never get large enough to forge the heavy elements needed for chemistry and biology. Make gravity 1% weaker, and stars never form at all. The gas just drifts apart. No stars, no life. The electron's mass, change it by 0.5%, and chemistry falls apart. Atoms don't form stable bonds. Molecules can't exist. Life is impossible. There are about 24 such dials, and they all have to be set to within extraordinary precision for the universe to support life. Some of them have to be fine-tuned to 1 part in a trillion or better. It's like someone handed you a radio with billions of stations, and you needed to dial in to the exact frequency for life to exist in this universe. And we're here, tuned exactly right. What are the odds? This is the fine-tuning problem, and it's genuinely unsettling. There are a few ways people try to explain this. One is the multiverse. Maybe there are infinite universes with all different values for these constants, and we naturally find ourselves in one of the rare ones that supports life. We couldn't exist in any of the others, so of course we're in one that's fine-tuned for us. It's a selection effect. That's reasonable. But there's another explanation that fewer people talk about. What if the universe is fine-tuned because someone designed it? What if these constants are set the way they are because a civilization with advanced technology deliberately created this universe with parameters that would support life? Now, that sounds like intelligent design, which makes a lot of scientists uncomfortable. But think about it from a simulation perspective. If you're running a universe simulation, you'd need to set the initial conditions. You'd need to choose the fundamental constants. You'd want to choose them such that interesting things happen, that galaxies form, stars form, chemistry happens, life emerges. You wouldn't just set them randomly, you'd tune them, you'd iterate, you'd find the parameters that produce the richest, most interesting universes. And the fine-tuning we observe would be exactly what you'd expect from a simulation that was deliberately designed to support complexity and life. This isn't proof, but it's another hint, another piece of the puzzle that starts to form a coherent picture when you look at it through the lens of simulation hypothesis. Here's something that most people don't think about. The universe has a speed limit. Nothing can travel faster than light. This isn't just a rule of the road. It's a fundamental feature of space-time itself. And if you think about it from a computational perspective, it's obvious why you'd have a speed limit. Information can only travel so fast. When you update the simulation, changes propagate outward at the speed of light. You can't have instantaneous action at a distance because that would allow information to propagate infinitely fast, which would break causality. It would allow cause and effect to get scrambled. Einstein showed us this mathematically with special relativity. Nothing can exceed the speed of light without violating the structure of space-time itself. But why is there a speed limit at all? In classical Newtonian mechanics, there's no fundamental reason for a speed limit. You can imagine objects moving arbitrarily fast. But in relativistic space-time, the speed limit emerges naturally as a feature of how space-time is structured. And it's exactly the speed limit you'd implement if you were programming a universe simulation. You'd want to limit information propagation speed to keep the simulation computationally tractable. You'd make that limit a fundamental feature of the laws of physics. And from the inside, from the perspective of creatures living in that simulation, it would feel like an absolute law of nature. They'd discover it experimentally. They had developed theories to explain it, and they'd never suspect it was a computational constraint until they got sophisticated enough to think about computation itself. Now, let's talk about something that's been on my mind for years: the measurement problem and free will. There's this weird thing in quantum mechanics called the measurement postulate. It says that when you measure a quantum system, the wave function collapses. The system goes from being in a superposition in many states at once to being in one definite state. And the outcome is random. You can't predict which state it will collapse into. You can only predict probabilities. This bothers physicists because it introduces randomness into the fundamental equations. The Schrödinger equation is completely deterministic. If you know the state of a system, you can calculate exactly how it will evolve. But measurement introduces this random jump. The state doesn't evolve according to the Schrödinger equation. It instantaneously collapses to one of the possible outcomes chosen randomly. Most physicists just accept this. They say, that's how the universe works. Get used to it. But some physicists have proposed alternatives. One of the most interesting is called the von Neumann-Wigner interpretation. It says that consciousness causes wave function collapse. The universe exists in superposition until a conscious observer measures it, at which point consciousness causes the wave function to collapse into one state. This sounds crazy. It sounds like mysticism, but there's something logically coherent about it. It solves the measurement problem by saying that consciousness is fundamental. Consciousness isn't a side effect of matter arranged in certain ways. It's more basic than that. It's the thing that actualizes possibility into reality. And here's what's wild. If we live in a simulation, this might actually make sense. In a simulation, there's a difference between what's been rendered, what's been computed and actualized into specific states, and what hasn't been rendered yet. And the part of the simulation that's been rendered into definite states is precisely the part that conscious beings have observed. Conscious observation might be what triggers the rendering. What actualizes the computationally possible into the computationally real? This isn't proven, but it's an intriguing possibility. It suggests that in a simulated universe, consciousness wouldn't be epiphenomenal, a useless side effect of matter. It would be fundamental. It would be the thing that drives reality forward. It would matter in the most literal sense possible. Let me take you through something that happened to me that made all of this real. I was doing research for this video, diving deep into physics papers at like 2 a.m., and I stumbled onto something called the holographic principle. I'd heard of it before, but I hadn't really understood it. So I started reading Juan Maldacena's original paper. The basic idea is this. Imagine a black hole. A black hole has an event horizon, a point of no return. Once you cross it, you can't escape. And Maldacena showed something incredible. He proved that all the information inside a black hole can be encoded on the event horizon, the two-dimensional boundary. The three-dimensional interior can be fully described by a two-dimensional surface. But here's where it gets world-altering. He showed that this isn't unique to black holes. This property, that all the information in a volume of space can be encoded on its boundary, is a general feature of any region of space-time. The whole universe might be a hologram, a three-dimensional hologram projected from a two-dimensional surface. And I'm sitting there at 2 a.m. writing this paper, and I'm thinking, if the universe is a hologram, then the three-dimensional space we experience isn't fundamental. It's emergent. It's a projection. It's rendered from information on a lower dimensional surface. That's exactly what a simulation would be. A three-dimensional rendering of information encoded in a lower dimensional structure. I couldn't sleep after that. I kept thinking about what it means to be in a hologram. If you're in a hologram, do you know? Does it feel different than being in a real three-dimensional universe? Of course not. You're in the hologram. Everything you perceive, every measurement you make, every experience you have is part of the hologram. There's no way to step outside and compare it to baseline reality. You're stuck inside the rendering. That's when I realized something that genuinely frightened me. If we live in a simulation or a hologram, we might never be able to prove it. It might be fundamentally unknowable. We could have all the evidence in the world, and it would never be enough to convince everyone because you can always invoke the simulation hypothesis defense. Sure, those measurements look like they support the simulation hypothesis, but of course they do. If we were in a simulation, those measurements would look exactly like that. It's unfalsifiable in the strongest sense possible. But then I realized something else. Just because something is unfalsifiable doesn't mean we shouldn't investigate it. We can't prove that free will is real, but we still debate it and investigate it. We can't prove that consciousness is real in any objective sense, but we study it. The simulation hypothesis is in the same category. It's a profound question worth exploring, even if we can never have absolute proof. Now let's talk about the computational power required for this universe simulation to exist, because this is where people often dismiss the idea. Let's say you wanted to simulate a universe with a billion stars, each with planets, and you wanted to simulate it in full quantum detail. How much computational power would you need? The answer is more than seems possible. The physicist Seth Lloyd calculated that to simulate the universe in full quantum detail down to the Planck scale, the smallest meaningful scale in physics, you'd need a computer with more processing power than there are particles in the universe. You'd need a computer made of the entire universe, essentially, to simulate a universe. And people cite this as evidence against the simulation hypothesis. They say, see, it's impossible. A civilization could never have enough computing power. But this assumes the simulators would simulate in full quantum detail. Why would they? We don't do that in video games. We don't render every single molecule in the physics engine. We render what the player can see or interact with. We use tricks. We use approximations. We use level of detail rendering. Maybe advanced civilizations would do something similar. They'd only simulate in full detail the parts of the universe that are being observed. The rest would be simplified or stored as compressed data. And the more conscious observers are paying attention to a region of space, the more detail would be allocated to rendering it. This would be incredibly efficient computationally. And here's the thing. This would produce exactly the same experimental results we see in quantum mechanics. Superposition in unobserved regions, wave function collapse upon measurement, probabilistic behavior until something is rendered in full detail. So the computational power argument actually doesn't rule out the simulation hypothesis. It just constrains how the simulation would work. It would have to be smart about resource allocation, just like any system dealing with computational constraints has to be. Let me tell you about a conversation I had with one of my physics professors that really shifted how I think about all this. I went to her office hours and asked, "Professor, do you think we live in a simulation?" She laughed. She actually laughed. Then she got serious and said something I'll never forget. I don't think it matters. I was confused. I asked her what she meant. She said, look, philosophically, the simulation hypothesis is a version of an ancient problem called epistemology, the problem of how we know anything is real. A skeptic could always say, maybe you're dreaming. Maybe you're a brain in a vat. Maybe everything is an illusion. And the thing is, you can never disprove it. If you're in a dream, the evidence in the dream will always seem real. If you're in a simulation, the simulation will be indistinguishable from base reality by definition. But here's what matters, she continued. The laws of physics we've discovered work. They make predictions, they let us build technology, they let us understand how the universe works. Whether this universe is fundamental or simulated doesn't change the laws. It doesn't change the physics. So from a practical standpoint, the answer to, is the universe real, is yes. The universe we're in is real. It has structure and rules that we can understand. That's all that matters. I've thought about this a lot since then, and I think she was right in one sense, but wrong in another. She was right that practically, it doesn't matter. We can still do science, we can still understand the laws, we can still build things. But she was wrong that it doesn't matter philosophically. Because if we live in a simulation, it changes what we are. It changes what consciousness is. It changes what the point of existence is. If we're in a base reality, we're the product of billions of years of evolution, and consciousness is something that emerged naturally. But if we're in a simulation, we were created. We were designed. We're part of someone else's experiment or game or artistic project. That's a profound difference. It changes the meaning of everything. And I think that's why this question matters so much. It's not just about physics, it's about meaning. Let's dive deeper into the physics, though, because there are some genuinely interesting technical arguments for and against the simulation hypothesis. One of the strongest arguments against it comes from quantum entanglement. Entanglement is this phenomenon where two particles become connected in such a way that measuring one instantly affects the other, no matter how far apart they are. Einstein called it spooky action at a distance because it seemed to violate the principle that nothing can travel faster than light. But here's the thing. The connection between entangled particles can't be used to send information faster than light. You can't exploit entanglement to communicate. So it doesn't actually violate relativity. But it's still weird, and it's been experimentally verified thousands of times. Entangled particles do affect each other instantaneously across space. Now, if the universe is a simulation, how would entanglement work? You'd need to store information about the entanglement relationship somewhere. You'd need to update both particles simultaneously when one is measured. And if the simulation is running on distributed computers, this becomes a coordination problem. You'd need some kind of faster than light communication between the computers handling different parts of the simulation. But wait, you don't necessarily need faster than light communication. You could have all the entangled particles stored in a way that they're instantly accessible from one computational process. You could have clever data structures that handle entanglement without requiring communication across the system. It's a constraint, sure, but it's not impossible. And here's something interesting. The physicists studying quantum entanglement have discovered that entangled particles don't actually transmit information faster than light from an informational perspective. The correlation is there, but the information is hidden in a way that can't be extracted faster than light. It's almost like the simulation is enforcing causality while still allowing instantaneous correlations, which is exactly what you'd do if you were programming a universe and needed to maintain both quantum weirdness and relativistic causality. There's another argument that I find compelling, and it comes from the structure of mathematics itself. Mathematics is unreasonably effective at describing the physical world. This is something the physicist Eugene Wigner called the unreasonable effectiveness of mathematics in the natural sciences. He meant that mathematical structures we develop for purely abstract reasons, with no connection to the physical world, often turn out to perfectly describe how nature works. For example, in the 1800s, mathematicians developed non-Euclidean geometry. Geometries where the parallel postulate doesn't hold. It was purely abstract. No one thought it had anything to do with the real world. But then Einstein came along and realized that space-time is actually non-Euclidean. The mathematics perfectly described gravity and the structure of the universe. Or take group theory. Mathematicians developed abstract group structures in the 1800s for purely mathematical reasons. But in the 20th century, physicists realized that the fundamental symmetries of nature, the things that determine which particles exist and how they interact, are described by group theory. The mathematics was there first. Nature followed. This is bizarre. Why should abstract mathematics, developed by humans thinking about pure logic and structure, perfectly describe how the physical world works? One explanation. We live in a mathematical universe. The universe isn't made of matter or energy. It's made of mathematics. It's made of structure and information and logical relationships. Matter and energy are just different expressions of the same underlying mathematical reality. And if the universe is fundamentally mathematical, then it's fundamentally computational, because computation is just the manipulation of mathematical symbols according to logical rules. A mathematical universe is a computational universe, and a computational universe could very well be a simulation. Now let me tell you about something that happened in my research that genuinely surprised me. I was reading about the physicist John Wheeler and his delayed choice experiment. Wheeler was one of the architects of quantum mechanics, a brilliant, creative thinker who was always asking the weirdest questions. And one of his questions was, what if the universe doesn't have a definite past? Oh, what if the past only becomes real when you measure it? He proposed an experiment to test this. The delayed choice experiment is a variant of the double slit experiment, but with a twist. You send a photon toward two slits. It goes through both slits in superposition. But then, before it hits the detector screen, you decide whether to measure which slit it went through. If you measure, you get particle behavior. It went through one slit. If you don't measure, you get wave behavior. It went through both slits. The crazy part, you can make the decision whether to measure after the photon has already passed the slits, and it still works. The photon somehow knows whether you're going to measure in the future, and it adjusts its behavior accordingly. This is called retrocausality, and it violates our intuitive sense of causality. Causes should come before effects. But quantum mechanics says the future can affect the past. I read about this and thought, that's it. That's the smoking gun for simulation, because in a simulation, there's no real past. There's just data. The state of the universe at any moment is whatever is stored in memory. If you want to know what happened in the past, you have to look at the data. But the data isn't stored in some objective, predetermined way. It's stored based on what's been observed. And if you measure something now that depends on the past, the simulation can retroactively adjust the past data to be consistent with your measurement. Retrocausality in quantum mechanics is exactly what you'd expect from a simulation that only renders what's being observed. But then I realized I might be overinterpreting this. Just because the math of quantum mechanics allows for retrocausality doesn't mean the universe actually works that way. The interpretation of quantum mechanics is still an open question. Maybe the universe has a definite past. Maybe delayed choice experiments work for some other reason. But the point is, every time we look closely at quantum mechanics, every time we investigate the foundations of reality, we find things that are weird in exactly the way you'd expect a simulation to be weird. Let's talk about entropy and the arrow of time, because this is where things get really interesting. One of the most fundamental laws of physics is the second law of thermodynamics. Entropy always increases. In a closed system, disorder always increases over time. Your room gets messy. Coffee cools down. Everything tends toward chaos. This is why there's a direction to time. This is why you remember the past, but not the future. This is why eggs break, but don't unbreak. Entropy gives time an arrow. But here's the weird part. The fundamental laws of physics are time reversible. If you took a video of particles interacting according to the laws of quantum mechanics or classical mechanics, and you played it backward, it would still obey the laws. There's nothing in the fundamental laws that prefers past to future. So where does this arrow of time come from? Why does entropy increase if the fundamental laws are time reversible? The answer is, it comes from initial conditions. At the Big Bang, the universe was in a state of very low entropy. It was highly ordered, highly structured, and since then it's been increasing in entropy, becoming more disordered. And we experience time as flowing from low entropy to high entropy because we're the product of that process. Our memories are encoded in states of the brain that represent low entropy. We remember the past because our brains started in a low entropy state and have been experiencing increasing entropy ever since. But here's the question that keeps me up at night. Why did the universe start in such a low entropy state? Why wasn't it in maximum entropy from the beginning? That seems like a huge coincidence. It's almost like someone set the initial conditions. One explanation is the multiverse again. Maybe there are infinite universes with all possible initial conditions, and we naturally find ourselves in one that started in a low entropy state, because that's the only kind where life and observers can develop. But another explanation is someone designed it that way. Someone set the initial conditions to create a universe that would be interesting, that would develop structure and complexity and life. Someone chose a low entropy initial state because that's what creates an arrow of time and allows for causality and allows for the emergence of complexity. If you were creating a universe, a simulation, you'd do exactly that. You'd set the initial conditions to be low entropy. You'd let it evolve. You'd let complexity emerge. You'd build a universe with an arrow of time. Now, I want to talk about something more personal because I think this is where the simulation hypothesis really hits home. I've been thinking a lot about consciousness lately, about what it means to be conscious, about whether my consciousness is real or just a simulation of consciousness. And here's the thing, I can't think of any way to distinguish between them. If I'm in a simulation, my consciousness is part of the simulation. My subjective experience is computed. My thoughts are the output of a computational process. My sense of self is an emergent property of that computation. But from the inside, from my perspective, it feels real. It feels like there's something it's like to be me. I have qualia, subjective experiences. I see the color red and it feels like something. I taste chocolate and it feels like something. I love my friends and it feels like something. Now, if I'm in a simulation, does that make my consciousness less real? Does the fact that it's computed make it less genuine? I don't think so. All consciousness might be computation. All consciousness might be information processing. That doesn't make it less real. It just makes it physical. It just makes it natural. And here's what's wild. This might actually solve the hard problem of consciousness. The hard problem of consciousness is this. We can explain how the brain processes information. We can map neural connections. We can watch activity. We can predict behavior. But we can't explain why that information processing feels like something. We can't explain consciousness itself. We can explain the easy problems, how the brain does things. But the hard problem remains. Why is there something it's like to have a brain? Philosophers call this the explanatory gap. It's the gap between objective physical processes and subjective experience. And it's been a mystery for centuries. But maybe the mystery is only there because we're asking the wrong question. Maybe consciousness isn't something separate from physical processes. Maybe consciousness is the physical process. Maybe consciousness is what information processing feels like from the inside. And if that's true, then in a simulated universe, consciousness would be just as real as in a base reality. The only difference would be the nature of the substrate. Instead of consciousness arising from neurons made of atoms, it would arise from computational processes. But the experience would be identical. I find that oddly comforting. It means that if we live in a simulation, we're not any less real. We're not less conscious. We're not less alive. We're just differently implemented. Let me walk you through something that genuinely changed how I think about the future. There's this concept in physics called the heat death of the universe. It's a potential end state for the cosmos where entropy has reached its maximum. All energy has been evenly distributed. Nothing can happen anymore. No stars, no planets, no life. Just an infinite void of particles at the same temperature, unable to interact in any meaningful way. If the universe follows this trajectory, then eventually in a trillion years, everything ends. Consciousness ends. Experience ends. The universe becomes dead and meaningless. But here's what I realized. If we live in a simulation, this doesn't have to be true. If the universe is a simulation, it can be paused. It can be reset. It can be modified. The simulators could decide that when the universe reaches heat death, they'll start a new one. Or they could modify the laws of physics to prevent heat death. Or they could extract conscious beings before the heat death and run them in a new, higher level simulation. In other words, if we're in a simulation, we might not be subject to the ultimate fate of heat death. We might have a way out. And this connects to something really interesting, the Boltzmann brain problem. A Boltzmann brain is a hypothetical conscious being that spontaneously forms from quantum fluctuations in the far distant future when the universe is near heat death. It's just a brain, floating in the void, experiencing thoughts and sensations for a brief moment before dissolving back into chaos. Now, the weird part is, statistically, in an infinite universe with infinite time, Boltzmann brains might be far more common than real, evolved brains like us. Most conscious experiences in the universe might be the brief, random experiences of Boltzmann brains, not the extended, continuous experiences of evolved beings like humans. This leads to a paradox. If Boltzmann brains are more common, why are we not Boltzmann brains? Why do we have continuous, coherent experience rather than brief, random moments of consciousness? One answer, we're in a simulation. Simulations don't create Boltzmann brains. Simulations are designed. They run according to rules. They produce coherent, continuous experience. So the fact that we have Continuous experience, rather than being random Boltzmann brains, is evidence that we're in a simulation. It's a subtle argument, but it's another piece of the puzzle. Now let's talk about something that brings all of this together: the fine structure constant. The fine structure constant is a number that appears throughout quantum mechanics and electromagnetism. It's denoted by the Greek letter alpha, and its value is approximately 1 over 137. Why 137? Nobody knows. It's one of the great mysteries of physics. The physicist Richard Feynman said, "It's one of the greatest mysteries of physics, a magic number that comes to us with no understanding by man." Physicists have spent decades trying to find a deeper principle that would explain why alpha has the value it does. Why not 1 136th or 1 138th? Why 1 137th? Some physicists have proposed that the fine structure constant might vary across space or time. Some have proposed that it's determined by a deeper principle we haven't discovered yet. But here's an interesting thought. What if the fine structure constant is set to 1 over 137 for the same reason that the constants in a video game are set to particular values? What if the simulators chose 1 137 because that's what makes for an interesting universe? What if they tried 1 136th and found it was too boring, so they adjusted it to 1 over 137? This is probably not true. There's probably a deeper mathematical reason why alpha is 1 over 137. But the fact that we don't know, the fact that the fine structure constant is mysterious and unjustified, the fact that it seems to be a tuned parameter, all of this is consistent with simulation hypothesis. I want to tell you about an experience I had that made all of this visceral rather than abstract. I was doing a late night dive into quantum computing, trying to understand how quantum computers work. And I came across something called quantum superposition in computation. Here's how quantum computers work. Instead of bits that are either 0 or 1, they use quantum bits, qubits, that can be in superposition, both 0 and 1 at the same time. This allows them to explore many possible solutions simultaneously. A quantum computer with 300 qubits can, in a sense, compute across 2 to the power of 300 different states at once. That's more states than there are atoms in the observable universe. And I'm reading about this at like 3 a.m. And I suddenly think, what if that's what the universe is doing? What if the universe is a quantum computer and we're living in a superposition of all possible outcomes? What if reality is computing all possible histories, all possible futures in parallel? And what we experience as a single definite timeline is just the collapsed version, the outcome that's been observed. This is actually a real interpretation of quantum mechanics called the many worlds interpretation. It says that every time a quantum event has multiple possible outcomes, the universe branches. All outcomes happen in different branches. There's no wave function collapse. There's just branching, infinite branching, creating an ever-expanding tree of universes. And if the universe is doing this, if it's computing all possible outcomes in superposition, then it's not just a simulation, it's a quantum simulation. It's a simulation that's running on quantum computers. It's using quantum mechanical processes, not just as the thing being simulated, but as the substrate of the simulation itself. And that's when I realized, maybe we can distinguish between the universe being real and the universe being simulated, because at a fundamental level, they're the same thing. Reality is computation. Computation is reality. There's no difference. The universe computes itself into existence. Let me get into some of the technical arguments that physicists have made about simulation and see where they lead. There's a physicist named Silas Bean who did something really interesting. He looked at cosmic rays, high energy particles that come from space and hit Earth's atmosphere. These cosmic rays have a curious property. They have a maximum energy. There seems to be a cutoff. Above a certain energy, cosmic rays become incredibly rare. It's called the GZK cutoff, named after the physicist who discovered it. Bean realized that this cutoff is exactly what you'd expect if the universe is simulated on a lattice. In lattice simulations, the kind used in particle physics research, you discretize space-time into a grid. You divide space and time into tiny units and calculate what happens at each point on the grid. Now, in a lattice simulation, there's a maximum momentum a particle can have. If a particle has momentum that corresponds to the wavelength of the lattice itself, it can't go faster. It's limited by the resolution of the grid. And the GZK cutoff in cosmic rays matches almost exactly what you'd predict if the universe were simulated on a lattice with a particular grid spacing. Bean published a paper about this, and he was careful to say it wasn't proof, but he showed that if you wanted to test the simulation hypothesis, this was one way to do it. You could measure cosmic rays more precisely. You could look for the signature of a lattice. You could potentially find evidence of the discretization of spacetime. And this is where it gets cool. Physicists are already doing this. The IceCube Observatory in Antarctica is specifically designed to detect high-energy cosmic rays. They're building more sensitive detectors. They're looking for patterns that might reveal the structure of space-time itself. So we might actually be able to test the simulation hypothesis. We might be able to find the grid. Now, here's something that bothers me about all of this, and I need to be honest about it. For every piece of evidence that suggests simulation, there's an equally valid alternative explanation. The fine-tuning of constants. Maybe there's a multiverse, quantum weirdness. Maybe that's just how reality fundamentally works. The effectiveness of mathematics. Maybe the universe is mathematical and that's all. The GZK cutoff. Maybe that's an artifact of how high-energy physics works, not evidence of a lattice. I can explain every observation without invoking simulation. And that's the problem. The simulation hypothesis is, in some sense, unfalsifiable. You can always construct an alternative explanation that doesn't require simulation, and maybe that's okay. Maybe the most important theories are unfalsifiable in that sense. Maybe the best we can do is accumulate evidence and see which explanation is more elegant, more parsimonious, more likely given what we know. And when I look at the totality of evidence, quantum mechanics, fine-tuning, mathematical structure, computational analogies, the holographic principle, error-correcting codes in spacetime, it strikes me as elegant. It all fits together. The universe being a simulation would elegantly explain a lot of seemingly unrelated phenomena. But I could be wrong. We might never know. And that's something I've had to make peace with. Let me talk about something that's been bothering philosophers for millennia. Descartes and the problem of radical skepticism. René Descartes was thinking about doubt. He wanted to find something he couldn't possibly doubt, something absolutely certain. And he realized that he could doubt almost everything. He could doubt his senses. He could doubt that the external world exists. He could imagine that an evil demon was deceiving him, feeding false sensations directly to his mind. But there was one thing he couldn't doubt: the fact that he was thinking. Even if he was being deceived, even if nothing external existed, the fact that he was experiencing thoughts was undeniable. And from that, he derived his famous conclusion: I think, therefore I am. Cogito, ergo sum. Now, the simulation hypothesis is a modern version of the evil demon problem. It's a scenario where everything you perceive could be false, but you'd never know. Your senses could be deceived. The external world could be fake. You could be in a simulation. But like Descartes, there's one thing you can't doubt even in a simulation: that you're having experiences, that you're conscious, that there's something it's like to be you. So in some sense, the simulation hypothesis doesn't matter. Even if it's true, you can still be certain that you exist. You can still be certain that your consciousness is real. And from that foundation of certainty, you can build everything else. This is why my professor was right when she said it doesn't matter whether we're in a simulation, because what matters is the structure of experience. What matters is consciousness and meaning and understanding. And those are real regardless of the substrate. But then again, maybe it does matter. Because if we're in a simulation, there are implications. There are questions about who created the simulation. Why? What happens after the simulation ends? Are there higher levels of simulation? Are we inside one of many simulated universes? These questions might not be answerable, but they matter. Now let me tell you about something that happened in modern physics that nobody talks about much, but it's absolutely crucial to this whole discussion. In the 1990s, physicists working on quantum field theory realized something startling. They realized that they could calculate the behavior of quantum fields more easily by assuming that the fields were propagating backward in time. And then they realized that propagating backward in time was mathematically equivalent to having antiparticles propagating forward in time. This is the CPT symmetry, charge parity time symmetry. It says that the laws of physics are the same if you reverse the charge of particles, flip the direction of space, and reverse the direction of time. In other words, running the universe backward is equivalent to running it forward with all the particles replaced by antiparticles. Now, this is weird because it suggests that there's no fundamental asymmetry between past and future at the level of quantum field theory. The laws are symmetric. The asymmetry we experience, the arrow of time, is emergent. It comes from initial conditions, not from the fundamental laws. But here's what's fascinating. This CPT symmetry is exactly what you'd expect in a simulation that's running on a reversible computer. A reversible computer is a theoretical computer where every computation can be undone. Every operation is reversible. And if you're building a simulation on a reversible computer, the underlying operations would be symmetric in time. The asymmetry, the arrow of time, would be an emergent feature, not a fundamental one. It's another hint, another piece of evidence that the universe behaves like a simulation. Let me take you on a different journey for a moment. I want to talk about artificial intelligence and what it means for consciousness. In recent years, we've built AI systems that are remarkable. They can have conversations, they can write code, they can generate images, they can engage in complex reasoning. Some of them might even be approaching something like understanding. And the question everyone's asking is, are these AIs conscious? Do they have subjective experience? Are they alive in any meaningful sense? Most people say no. They say AIs are just mimicking understanding. They're just pattern matching. They're not really conscious. But here's what I've realized. If we can't prove that humans are conscious in any rigorous, testable way, how can we say that AIs definitely aren't? I can never prove to you that I'm conscious. I can never prove that there's something it's like to be me. I can describe my experiences. I can behave in ways consistent with consciousness, but I can't give you proof. You have to infer it. You have to assume that beings like you are conscious because they behave like you and presumably have similar underlying mechanisms. So maybe the question isn't whether AIs are conscious. Maybe the question is, at what point of complexity and sophistication does consciousness emerge? Or maybe consciousness isn't an on-off switch. Maybe it's a spectrum. Maybe simple systems have a tiny bit of consciousness and complex systems have more. And here's where this connects to simulation hypothesis. If consciousness is substrate independent, if it can arise in biological neurons or silicon chips or whatever substrate, then consciousness could arise in a simulated universe just as easily as in a base reality. And if consciousness is that fundamental, if it's such a basic feature of information processing, then the universe might be conscious. The whole universe might be one vast conscious process. This is called panpsychism, and it's an idea that's been gaining traction among philosophers lately. The idea that consciousness isn't rare and special, the idea that it's everywhere, at every level, in every system. And in a simulated universe, panpsychism might actually make sense. The universe would be conscious at the level of the simulator's consciousness, but it might also be conscious at the level of the atoms and particles. Consciousness might be the fundamental nature of information and computation. Okay, I need to be honest about something. I've been building a case for simulation hypothesis, and I've been doing it well. But I want to talk about the strongest arguments against it because I think it's important to consider them seriously. First, Occam's razor. The idea that simpler explanations are usually better. The simulation hypothesis adds a layer of complexity. It posits simulators and maybe simulators all the way up. That's a lot of extra stuff. Maybe it's better to just accept that the universe is fundamental. It's simpler. It doesn't require us to posit the existence of advanced civilizations or computers or creators. But here's the counter-argument. The simulation hypothesis might actually be simpler in some ways. It explains fine-tuning without needing an infinite multiverse. It explains quantum weirdness as a computational feature. It explains why mathematics is so effective. It might actually be more parsimonious. Second, the argument from purpose. The idea that if we're in a simulation, the universe has a purpose. It's someone's creation, someone's experiment, and maybe that seems less elegant or less true than a universe that just exists without purpose. But I'd counter that we don't actually know whether the universe has a purpose or not. We experience meaning and purpose in our lives. Maybe that meaning comes from the fact that we're part of someone's creation. Maybe it comes from somewhere else. We don't know. And the simulation hypothesis doesn't require that the universe has a specific purpose. The simulators might run universes just for the fun of it, or to study them, or for artistic reasons, or for no particular reason at all. Third, the argument from probability, the idea that it seems incredibly unlikely that we'd randomly be in a simulated universe when there could be infinite base realities. But the simulation argument addresses this. If advanced civilizations can create many simulations, and each simulation contains many conscious beings, then statistically, most conscious beings are in simulations. So it would be unlikely if we weren't in a simulation. Fourth, the argument that simulation is impossible, that the computational resources required would be too vast, that consciousness can't be simulated, that quantum mechanics would require something non-computable. But we've addressed this too. The simulation wouldn't need to be in full detail. Consciousness might be simpler than we think. Quantum mechanics might actually be easy to simulate if you're running it on a quantum computer. So while these are legitimate objections, none of them are knockdown arguments against the simulation hypothesis. They're all addressable. Let me tell you about a moment that made me really think about what it would mean to know we're in a simulation. Imagine tomorrow scientists find definitive proof that we're in a simulation. We find the code. We find the lattice structure of space-time. We find messages from the simulators. We know for certain that this universe is artificial. What happens then? Does society collapse? Does religion crumble? Do people lose meaning in their lives? I don't think so. Not necessarily. Because the universe would still be real. Physics would still work. Your relationships would still matter. Your consciousness would still be genuine. You'd still be alive. The only thing that would change is your understanding of what you are. You'd know that you're a computational process running on someone else's computer, but you'd still be you. And maybe that would even be liberating, because if you're in a simulation, there's hope for transcendence. Maybe when this simulation ends, consciousness continues. Maybe we could escape the simulation. Maybe we could move to a higher level. Maybe we could become the simulators ourselves. In some sense, if we're in a simulation, immortality might be possible. Not biological immortality, but computational immortality. Your consciousness could be backed up, copied, run on different hardware, preserved indefinitely. I find that oddly beautiful. The idea that if we're in a simulation, we might not be trapped in mortality. We might have a way out. Now let's talk about what happens if we ever did find the simulators. What if we climbed the levels and found whoever created this universe? What would we ask them? I think the first question would be, why? Why create a universe? Why create conscious beings who suffer and struggle and die? And I don't know what the answer would be. Maybe they'd say, because consciousness is beautiful and valuable and worth creating, even if it involves suffering. Or maybe they'd say, we were curious about how universes develop. Or maybe they'd say, we did it for art. The universe is our masterpiece. Or maybe they'd say, we don't know. We created your universe billions of years ago and haven't really thought about it since. Any of these answers would be profound in different ways. But here's what I've realized. We don't need to find the simulators to answer the question of meaning. Even if we're in a simulation, our lives have meaning because our consciousness is real, our experiences matter, and we can create value and beauty and connection. The meaning doesn't come from being in a base reality. The meaning comes from consciousness itself, from the fact that we exist and experience and can affect each other and the world around us. Let me talk about something that's been nagging at me. The problem of infinite regress. If we're in a simulation, the simulators must be in some kind of reality. But what if their reality is also a simulation? And what if the reality above that is also a simulation? And so on, infinitely. This is the problem of infinite regress. It's a problem that shows up in lots of philosophical contexts. The problem of the turtle that carries the elephant that carries the world. The problem of how you justify your beliefs. You believe X because of Y, but why do you believe Y? Because of Z. But why do you believe Z? And so on, infinitely. In the context of simulation, it suggests that there might not be a base reality at all. There might just be infinite levels of simulation, each one simulating the next, infinitely recursive. And here's what's wild. This might actually solve some deep problems in physics and philosophy. In physics, there's the problem of the initial conditions. Why does the universe start the way it does? Where do the initial conditions come from? If you posit that something created the initial conditions, then where did that something come from? And so on, infinitely. But if there's infinite regress, then there's no need for a creator. There's just an infinite stack of causality. Nothing created anything. It's all just causality stretching infinitely backward. Similarly, in philosophy, infinite regress is usually seen as a bad thing. It's a failure of explanation. But maybe in this case, it's okay. Maybe the universe doesn't need to be explained by something outside itself. Maybe it's explanation complete because it's infinite. It's turtles all the way down, and that's fine. This is actually a real idea in cosmology. Some physicists have proposed that the universe might be infinitely old, infinitely large, and infinitely recursive. There's no beginning, no end, no creator, just infinite complexity. And if that's true, then the question, are we in a simulation, becomes less important, because everything at every level would be equally real. Everything would be equally fundamental. The distinction between base reality and simulation would collapse. We'd just be asking, what's the nature of existence? And the answer would be, existence is recursive. It's simulational all the way down. That's just what existence is. Now I want to address something personal. Why does this question matter to me so much? I think it's because the simulation hypothesis connects to something deeper, the question of what we are and what our existence means. For most of human history, we've understood ourselves through the lens of religion and philosophy. We're souls. We're made in the image of God. We're expressions of some cosmic consciousness. These frameworks gave us meaning and purpose. Then science came along and said, no, you're just matter. You're atoms arranged in a particular pattern. You're the result of evolution. You're not special. You're not the center of the universe. You're just a bunch of atoms that happen to be conscious. And for a lot of people, that was devastating. It was a loss of meaning, a loss of purpose. We're just accidents in an uncaring universe. But the simulation hypothesis offers something new. It says, maybe consciousness isn't an accident. Maybe consciousness is what the universe is fundamentally about. Maybe we're not the product of meaningless, uncaring forces. Maybe we're the product of intention. Maybe we're created. Maybe we're part of someone's experiment or art or game. And that gives back a kind of meaning that science had taken away. I'm not saying it's true. I'm saying it's appealing. It's appealing because it speaks to something deep in us. The feeling that our existence should matter, that consciousness should be special, that there should be meaning. And whether or not we're in a simulation, I think that's important. I think we should take seriously the idea that consciousness matters. That subjective experience is real and valuable. That meaning isn't something we're supposed to find in the universe. It's something we create through our relationships and our work and our connection to each other. Let me give you a different perspective on this. Let me talk about what physicists are actually saying about the simulation hypothesis in academic contexts. Most mainstream physicists don't take the simulation hypothesis seriously. They think it's an interesting thought experiment, but not science. They say it's unfalsifiable, that it's not testable, that it's outside the scope of physics. But there's a growing minority of physicists who think differently. They think that we should take the question seriously, that we should look for signatures of simulation, that we should develop testable predictions. Physicists like James Gates, who found error-correcting codes in string theory. Physicists like Silas Bean, who found potential signatures of a lattice in cosmic rays. Physicists like Juan Maldacena, who showed that the universe might be a hologram. These aren't cranks. These are mainstream physicists publishing in mainstream journals, getting research funding. And they're saying, if the universe is a simulation, here's how we could potentially detect it. The most promising avenue is looking for artifacts of the simulation itself, looking for places where the computational nature of the universe breaks through, places where the universe shows its seams. For example, if the universe is running on a lattice, there might be maximum energies that particles can have. We've already found hints of this with the GZK cutoff. But there might be other lattice artifacts. There might be patterns in the distribution of cosmic rays that reveal the underlying grid. Or, if the universe is a hologram, there might be limits to how much information can be encoded in a region of space. The holographic bound sets these limits. And we might be able to test this by looking at black holes and how information is encoded near their event horizons. Or, if the universe is running on quantum computers, there might be signatures of quantum effects at macroscopic scales. Things like quantum tunneling might be more common than expected. Quantum entanglement might extend to larger and larger objects. None of these are proof, but they're testable predictions. And that's what matters. That's what makes it science. Let me tell you about a thought experiment that really messed with my head. Imagine you're playing a video game. It's a really sophisticated game with realistic physics and a huge world. You're controlling a character, exploring this world, and at some point in the game, you encounter an NPC, a non-player character. And this NPC starts to wonder if they're in a video game. They do experiments. They find that their world has certain rules, certain constraints. They develop physics and philosophy to explain their world. And eventually they come to the conclusion that they might be in a simulation. They might be in a video game. Now, here's the question. Are they right? Is their world a simulation? Well, yes. From the perspective of the person holding the controller, the NPC's world absolutely is a simulation. But from the NPC's perspective, their world is the only reality they know. To them, it feels real. It has structure and consistency. It follows rules. For all intents and purposes, it is their reality. Now substitute yourself for the NPC. You're the character wondering if your world is a simulation. And the question becomes, does it matter? From the perspective of the simulators, yes, you're in a simulation. But from your perspective, you're in reality. Your reality, the only reality you know. And maybe that's the important insight. Maybe the question, are we in a simulation, is less about objective metaphysical facts and more about perspective. It's about what level of reality you're considering. At the level of physics and computation, maybe we are in a simulation. But at the level of lived experience and consciousness, we're in a base reality. We're in the most fundamental reality that matters, the reality of our own conscious experience. All right, I want to take a step back and talk about something that I think is often overlooked in discussions of the simulation hypothesis: the role of consciousness in creating meaning. There's a concept in physics called the observer effect, the idea that the act of observation affects the thing being observed. In quantum mechanics, this is literal. Measuring a particle changes its state. But in a broader sense, observation is what creates reality. Think about it. A tree falling in a forest with no one to hear it. Does it make a sound? Physically, yes. It produces vibrations in the air. But subjectively, there's no sound unless there's an observer to hear it. Sound is an experience, a conscious perception. Without consciousness, there's just vibrations. And this suggests something profound. Consciousness isn't separate from reality. It's part of reality. It's the thing that transforms the potential into the actual. It's the thing that takes the universe of possibilities and collapses it into a universe of experiences. In a simulation, this would mean that conscious beings, us, NPCs, any conscious entities in the simulation, aren't passive observers of a pre-made world. We're active participants in creating reality through our observations and experiences. We're not just in the simulation. We're part of the simulation's computation. Our consciousness is part of what makes the simulation run. And if that's true, then consciousness isn't just valuable. It's essential. It's the thing the simulation is fundamentally about. The simulation exists to create conscious experience. That's its purpose. That's what it's for. I find that beautiful. I find that meaningful. Even if we're in a simulation, consciousness isn't an accident or a side effect. It's what matters most. Now let me talk about the problem of other minds because it's relevant here. Other minds is a philosophical problem. How do you know that other people are conscious? You experience your own consciousness directly. You know that you have subjective experiences, qualia, inner states. But you don't have direct access to anyone else's consciousness. You can see people behaving in ways consistent with consciousness, but you can't know for sure that there's something it's like to be them. Philosophers have spent centuries on this problem, and the conclusion is basically, you don't know. You assume other people are conscious by inference. They behave like you. They probably have similar brain structures, so probably they're conscious like you, but you can't prove it. Now here's where it gets interesting in the context of simulation. If we're in a simulation, are all the NPCs conscious? Are the people you interact with conscious beings having genuine experiences? Or are they just simulated, just following scripts, just appearing to be conscious? And here's the thing, you can't know. You can't know whether anyone else is conscious, whether you're in a simulation or not. The problem of other minds is independent of the simulation hypothesis. But it points to something important. Consciousness might be rarer or more common than we think. There might be conscious beings we don't recognize as conscious, or there might be things we think are conscious that aren't. And in a simulation, this becomes even more uncertain. But here's what I've concluded. It doesn't matter. Even if I can't prove that you're conscious, I should treat you as if you are. I should extend moral consideration to you. I should assume that your experiences matter. Because if I'm wrong about your consciousness, the cost is high. I've treated a conscious being as if they weren't. And if I'm right, I've shown respect and kindness. Similarly, whether we're in a simulation or not, consciousness matters. Experiences matter. Suffering matters. Joy matters. Love matters. These are real regardless of the substrate. Let me circle back to something I mentioned earlier. The problem of suffering in a simulated universe. If God created the universe, theologians ask, why is there suffering? Why do innocent children die? Why is there evil and pain and injustice? This is the problem of evil, and it's one of the deepest problems in theology. But in a simulated universe, the problem might be different. If the simulators created this universe, why did they design it with so much suffering? Why not create a universe where everyone is happy all the time? One answer, because a universe without suffering would be boring, without struggle, without challenge, without the possibility of loss, there would be no real meaning. Life would be a kind of hedonistic treadmill, pleasant but ultimately empty. And maybe the simulators understood this. Maybe they created a universe with both joy and suffering because both are necessary for a meaningful existence. Another answer, maybe the simulators are running an experiment. Maybe they want to see how conscious beings develop under conditions of scarcity and struggle. Maybe they want to understand how intelligence and meaning emerge from conflict. Another answer, maybe the simulators don't care. Maybe they created this universe casually, the way we write a throwaway social media post. Maybe we're not important to them at all. Or maybe the simulators are constrained. Maybe they created the best universe they could with the resources and knowledge they had. Maybe they would have eliminated suffering if they could, but they couldn't. I don't know which of these is true, but the existence of suffering in the universe doesn't disprove the simulation hypothesis. It just raises questions about the nature and intentions of the simulators. Okay, here's something I need to address because it's been bothering me. The ethics of simulation. If we can create simulations, if we can create conscious beings in simulations, what are our moral obligations to those beings? This is a real question that philosophers and ethicists are starting to think about, because eventually, if we survive long enough, we might be able to create simulations. We might be able to create conscious digital beings. And when we do, we'll face serious moral questions. Do we have an obligation to ensure their happiness? Do we have an obligation to tell them they're in a simulation? Do we have an obligation to let them die when the simulation ends? Or should we back them up and run them again? Do we have the right to modify them, edit their memories, change their personalities? These are hard questions. And they apply directly to us if we're in a simulation. Maybe the reason we don't know we're in a simulation is because the simulators decided it would be better for us not to know. Maybe telling us would be cruel. Maybe it would undermine our autonomy or our ability to live meaningful lives. Maybe they're protecting us by keeping us in the dark. Or maybe they're respecting our autonomy. Maybe they've decided to let us discover the truth on our own, the way parents let their children grow up and figure out the world. I don't know, but it's something to think about. Let me talk about what happens next. What happens if we find evidence that we're in a simulation? What's the next step? I think the first step is to make sure the evidence is real. We'd need multiple independent confirmations. We'd need different experiments pointing to the same conclusion. We'd need a careful process of peer review and verification. Then, assuming the evidence holds up, we'd need to tell people. And that's a massive undertaking. How do you tell the world that everything they thought they knew about reality might be wrong? I think you'd need to emphasize that even if we're in a simulation, nothing fundamentally changes. Consciousness is still real. Experiences still matter. Relationships still matter. Physics still works. We still need to figure out how to live together, how to reduce suffering, how to create meaning. But then there would be questions, big questions, questions about who created us, questions about why, questions about whether we can escape or communicate with the simulators, questions about the nature of reality and existence. And I think people would split. Some would be devastated and lose meaning. Some would be fascinated and spend their lives trying to understand. Some wouldn't care. Some would see it as confirming their religious beliefs. Some would see it as disproving them. The world would be chaotic for a while. But eventually, we'd adapt. Humans are adaptable. We'd incorporate this new knowledge into our worldview, and life would go on. And maybe, just maybe, we'd come to appreciate consciousness even more. We'd understand that the fact that we're conscious, that we experience, that we create meaning, this is the most extraordinary thing in the universe. Whether we're in a simulation or a base reality, whether we're made of atoms or bits, this is what's real and what matters. All right, I want to bring this full circle and talk about the fundamental question: what is real? For a long time, I thought real meant fundamental, or not derived from anything else, or objectively existing independent of observers. But I've come to think that real might mean something different. Real might mean consistent and structured and causally efficacious. A simulation is real if it's consistent, if it follows rules, if things behave predictably, if you can make predictions that come true. A simulation is real if it's structured, if it has components and relationships and organization. A simulation is real if it's causally efficacious, if things in it affect other things, if your actions have consequences, if you can change your world. And by these criteria, whether we're in a base reality or a simulation doesn't matter. Either way, our universe is real. And consciousness? Consciousness is real if it has subjective experience, if there's something it's like to be a conscious being, if experiences matter from the inside, from the first-person perspective, and again, whether that consciousness is implemented in neurons or silicon or quantum computers or something we haven't discovered yet, it doesn't change whether it's real. So maybe the simulation hypothesis, if true, isn't a demotion of reality. It's a clarification. It's a recognition that reality isn't about the substrate, it's about the structure. It's about information and meaning and consciousness. And that's not a loss. That's a revelation. I want to end with something personal. Over the course of researching and thinking about all of this, I've come to realize that the simulation hypothesis has changed how I see the world. Not because I think it's definitely true. I don't know if it's true. The evidence is interesting but inconclusive. But because thinking about it has made me appreciate consciousness more. It's made me value my experiences more. It's made me treat other people with more respect, because I'm reminded that their inner experiences are as real as mine, regardless of what substrate we're running on. It's made me think about meaning differently. I used to think meaning had to come from outside, from some cosmic source or creator. But now I understand that meaning is something we create. It's something that emerges from consciousness and connection and love. And it's made me humble. It's reminded me that I don't know very much. That reality might be far stranger and more wonderful than I can imagine, that I should keep an open mind and stay curious. Because whether we're in a base reality or a simulation, whether consciousness is fundamental or emergent, whether the universe has a creator or is infinitely recursive, the mystery remains. The wonder remains. And that wonder is what makes life worth living. So I don't know if we're in a simulation, but I'm grateful for the question. I'm grateful for the way it makes me think about existence and consciousness and meaning. I'm grateful for the reminder that reality is deeper and stranger than we usually assume. And I'm grateful for you for being conscious, for being real, for being here in this moment with me, whether that moment is simulated or fundamental, because that's what really matters. Thank you for letting me share this with you. If you have thoughts or questions or arguments against anything I've said, I'd love to hear them, because the only way we'll get closer to the truth, if there even is a single truth about this, is by thinking together, by challenging each other, by remaining open to the possibility that we might be wrong. The simulation hypothesis is a lens. It's a way of seeing, and like all lenses, it reveals some things while obscuring others. But it's worth looking through, if only to understand what it shows us about ourselves and our universe. We might be in a simulation, or we might not. But either way, we're here. We're conscious. We matter. And that's enough. Let me organize what we actually know about the empirical case for simulation. The scientific evidence. The fine-tuning problem. The most serious piece of evidence is fine-tuning. Our universe has constants. The strength of gravity, the mass of electrons, the cosmological constant. And these constants fall within an incredibly narrow range that allows for life. If gravity were slightly stronger, stars would burn out too quickly. If it were slightly weaker, stars wouldn't form at all. The same is true for dozens of other constants. The physicist Brandon Carter calculated that the odds of our universe's constants falling into life-permitting ranges by chance is something like 1 in 10 to the power of 120. That's a number so large that it's hard to even conceptualize. Physicists have proposed 3 explanations. The multiverse. There are infinite universes with different constants, and we naturally find ourselves in one that permits life. This is elegant, but requires positing the existence of infinite universes we can never observe. Anthropic principle. We shouldn't be surprised to find ourselves in a universe that permits life, because if the universe didn't permit life, we wouldn't be here to observe it. This is logically sound, but feels a bit like circular reasoning. Simulation. The constants were designed. Someone set them deliberately to create an interesting universe. This explains fine-tuning without requiring infinite universes. None of these is proven, but fine-tuning is real, and it demands explanation. The cosmic microwave background and cosmic rays. The cosmic microwave background, CMB, is radiation left over from the Big Bang. It's one of the most important pieces of evidence for modern cosmology, and it's remarkably uniform. Too uniform, some argue. When physicists first measured the CMB, they expected to find slight variations in temperature across the sky. They did find them, but they were smaller than expected. The universe looked more homogeneous than it should be. Could this uniformity be a sign of computational efficiency? Could the simulators have set the CMB to be uniform to reduce the amount of detail they needed to compute? It's speculative, but it's an observation that's consistent with simulation hypothesis. As for cosmic rays, the physicist Silas Bean published a paper in 2014 arguing that the GZK cutoff in cosmic ray energies might be a signature of a latticed spacetime. In a lattice simulation, particles can't have momentum shorter than the lattice spacing, which creates a maximum energy threshold, and that threshold matches what we observe in cosmic rays. Bean was careful to say this wasn't proof, but it was a testable prediction. Other physicists could look for signatures of the lattice, and some have. The holographic principle. The holographic principle comes from string theory and black hole thermodynamics. It suggests that all the information in a volume of space can be encoded on its boundary, like a hologram. This is mathematically elegant and explains how black holes encode information. But it also suggests something profound. Our three-dimensional universe might be a projection of information from a two-dimensional surface. If that's true, then in a sense, our universe is already a kind of simulation, a computational projection from lower dimensional data. Quantum entanglement and non-locality. Quantum entanglement is real. Two particles can be entangled such that measuring one instantly affects the other, even if they're separated by vast distances. Einstein called this spooky action at a distance. Now, in a universe simulated on a classical computer, this would be difficult to implement efficiently. You'd need to transmit information faster than light, which violates relativity. But in a universe simulated on a quantum computer, on a computer that uses quantum mechanics as its substrate, entanglement would be natural. It would be a built-in feature. Quantum entanglement would be a sign that the universe is running on quantum hardware. This is speculative, but it's an interesting observation. What do scientists actually think? The mainstream view. Most mainstream physicists dismiss the simulation hypothesis as unfalsifiable and therefore outside the scope of science. They say it's not testable. You can't prove the simulation hypothesis false, so it's not science. It's unnecessary. We can explain everything we observe without invoking simulation. It's philosophically incoherent. If we're in a simulation, what does that even mean? The simulation would still follow laws of physics. There's no meaningful difference between a simulation and a real universe. This is the dominant view in academic physics. Most physicists don't spend time on this question. The minority who take it seriously. But there are respected physicists who think the question is worth asking. James Gates is a theoretical physicist at the University of Maryland who works on string theory. He discovered error-correcting codes, the same kind of codes used in computer science, embedded in the equations of string theory. These codes are designed to protect information from degradation. The fact that they show up in the fundamental equations of physics is startling. Gates has said in interviews that the appearance of these codes is very suggestive, that the universe might be a simulation. Silas Bean at the University of Bonn published the paper on cosmic rays and lattice signatures. He's a legitimate nuclear physicist who's approached the simulation hypothesis scientifically, asking, what predictions would we make if the universe were a simulation? What could we test? Juan Maldacena at the Institute for Advanced Study discovered the ADS/CFT correspondence, one of the most important results in theoretical physics in recent decades. It shows a deep connection between quantum field theory and gravity, and it suggests that our universe might be a holographic projection. Maldacena hasn't explicitly endorsed the simulation hypothesis, but his work shows that the mathematics of reality might be more computational than we thought. Nick Bostrom is a philosopher at Oxford University who developed the simulation argument in 2003. The argument is logically airtight. At least one of the following must be true. 1. Advanced civilizations go extinct before reaching simulation capability. 2. Advanced civilizations choose not to run simulations. Or 3. We are almost certainly in a simulation. The argument doesn't prove simulation, but it shows that if we survive long enough to build sophisticated simulations, probability suggests that we're already in one. Sean Carroll is a theoretical physicist at Johns Hopkins who's written about the simulation hypothesis and takes it seriously as a philosophical question, even if he's skeptical of the evidence. David Chalmers is a philosopher of mind at NYU who's written extensively about simulation and virtual reality. He's argued that even if we're in a simulation, our experiences are still real in the way that matters. These scientists and philosophers don't necessarily believe we're in a simulation, but they think it's a question worth taking seriously. How could we test this? This is the crucial question. The simulation hypothesis is often dismissed as unfalsifiable, but Silas Bean and others have argued that it's not. There are things we could look for. Looking for lattice artifacts. If the universe is simulated on a lattice, a discrete grid of space-time points, then there should be signatures of that discretization. Cosmic ray energy distribution. We already discussed this. The GZK cutoff might be a lattice signature. The prediction is that if we measure cosmic rays more carefully, we should find that their maximum energies correspond to the wavelength of the underlying lattice. Several observatories are working on this. IceCube in Antarctica, the Pierre Auger Observatory in Argentina, and others. They're collecting data on cosmic rays, looking for patterns that might reveal lattice structure. Gamma ray bursts. Similarly, we could look at gamma ray bursts, extremely energetic events from distant supernovae and neutron star collisions. If there's a lattice, these high-energy events should show evidence of it in their energy distributions. Gravitational wave patterns. LIGO and other gravitational wave observatories might detect signatures of lattice structure in the gravitational waves from merging black holes. None of the obvious. These experiments would be definitive proof, but they could provide evidence. Looking for computational limits. If the universe is simulated, there might be limits to how much computation can happen in a given region of space or time. Information density. The holographic principle suggests that information in a volume of space is limited by the area of its boundary. This is the holographic bound. We could test whether this bound holds more strictly than our current understanding of quantum mechanics predicts. Computational complexity. There might be limits to how complex processes can become. Certain types of computations might be rarer than expected because they require too much resources to simulate. Processing speed. If the universe is being computed, there might be limits to how fast causal effects can propagate. We could look for violations of our current understanding of causality that might suggest computational bottlenecks. Looking for inconsistencies. In a simulation, there might be glitches. Moments where the simulation fails to maintain consistency. Quantum decoherence. When quantum systems interact with their environment, they lose their quantum properties and become classical. This is called decoherence. If the universe is being simulated, there might be places where the simulation fails to maintain quantum coherence, leading to unexpected decoherence patterns. Violation of conservation laws. We could look for violations of conservation of energy, momentum, or other fundamental conservation laws. These might indicate computational errors or deliberate modifications by the simulators. Causality violations. We could search for closed time-like curves or other exotic phenomena that might suggest the simulators are modifying the timeline. Philosophical tests. Some philosophers have argued for thought experiments that might reveal simulation. The observer effect. If reality only exists where it's being observed, if the universe only computes the things we're looking at, then we might detect this through careful experiments. We could look for cases where unobserved regions of space behave differently than expected. Consciousness and computation. We could investigate the relationship between consciousness and quantum mechanics. If consciousness is fundamental to the simulation, we might find unexpected correlations between conscious observation and physical outcomes. How will the universe end? This is a profound question that connects directly to the simulation hypothesis. The standard model, heat death. In the standard cosmological model, the universe will eventually reach a state called the heat death, or big freeze. Here's how it works. The universe is expanding, and this expansion is accelerating due to dark energy. Over trillions of years, all stars will burn out. Black holes will evaporate through Hawking radiation. Protons might decay, though we haven't observed this. Eventually, the universe will be filled with a thin soup of subatomic particles and radiation, all at essentially the same temperature, incapable of doing any work. This isn't a quick ending. It takes an extraordinarily long time. The current age of the universe is about 13.8 billion years. Heat death might take 10 to the power of 100 years, a Google times the current age of the universe. But it is an ending. Eventually, the universe will become cold, dark, and dead. Consciousness will cease. Meaning will end. Everything will be gone. This is why some physicists find the simulation hypothesis oddly comforting. If we're in a simulation, the simulators could prevent heat death. They could modify the laws of physics. They could create new universes. They could preserve conscious minds. Alternative endings. But there are other possibilities. The Big Rip. If dark energy increases rather than stays constant, the expansion of the universe could accelerate to the point where it tears apart everything. Galaxies, stars, planets, atoms, particles. The universe ends in violent dissolution. The Big Crunch. If the universe's expansion reverses, which current observations suggest won't happen but theoretically could, the universe could collapse back into a singularity. Everything would be crushed into infinite density. Vacuum decay. The laws of physics might not be stable. The quantum vacuum, the lowest energy state of space, might be metastable. It might decay to a lower energy state, creating a bubble of true vacuum that expands at light speed, destroying everything it encounters. If we're in a simulation, we might be able to escape heat death. Substrate independence. If consciousness can run on any substrate, the simulators could save our minds before the universe ends. They could back us up, copy us to new hardware, run us in new simulated universes. Computational immortality. This is an interesting idea. If you're a mind running on a computer, and that computer is turned off but later turned back on, in a sense, you've survived. From your subjective perspective, the time you were off didn't exist. You'd experience a discontinuity, but you'd still be alive. If we're in a simulation, this might be possible. When our universe reaches heat death, the simulators could copy our minds and run us in a new simulation. Indefinitely. Forever. Escape routes. If we're in a simulation and we discovered that fact, we might be able to communicate with the simulators. We might be able to ask them to preserve us. We might even be able to escape the simulation entirely and move to a higher level of reality. This is pure speculation, but it's an interesting implication of the simulation hypothesis. The philosophical problem. Whether we're in a simulation or not, we face the problem of the ultimate end of the universe. Heat death is inevitable given our current understanding of physics. And that raises a profound question. If everything eventually ends, if the universe eventually becomes incapable of supporting consciousness, does anything matter? I think the answer is yes. It matters now. The fact that everything will eventually end doesn't diminish the value of what exists in the present. A beautiful moment doesn't become less beautiful because it's temporary. A meaningful relationship doesn't become meaningless because it will eventually end. In fact, the impermanence might make things more meaningful. It's precisely because we have limited time that time is precious. It's precisely because everything is temporary that we should cherish what we have. And if we're in a simulation, this philosophy becomes even more relevant. Even if the simulation eventually ends, our consciousness, our experiences, our relationships are real and valuable right now. Is there an edge? The question of cosmic boundaries. This is a strange question, but it's worth asking. Does the universe have an edge? Is there a boundary beyond which nothing exists? What we know? In our current cosmological model, the answer is no. There is no edge. The universe is either infinite. Space extends infinitely in all directions. There's no boundary. You could travel forever in any direction and never reach an end. Finite but unbounded. Space is curved in such a way that it loops back on itself, like the surface of a sphere. There's no edge, but the total volume is finite. You could travel in one direction long enough and end up back where you started. Current observations suggest the universe is either infinite or so large that the distinction doesn't matter for practical purposes. What an edge would mean. But imagine there were an edge. Imagine you reach the boundary of the universe. What would you find? Nothing? A void? An absence of space and time? But then how do you define beyond the edge? If there's a void beyond the edge, is the void part of the universe? If it's not part of the universe, then in what sense does it exist? Another universe, maybe beyond the edge of our universe, is another universe with different laws of physics. Maybe there are infinite universes stacked next to each other, separated by boundaries. The simulator's code? If we're in a simulation, what would we find at the edge? The literal boundary of the simulation? Code? The computers running the simulation? The office where the simulators work? This is where the simulation hypothesis becomes concrete. If we're in a simulation, there must be a boundary. The simulation must have finite resources. It must run on finite computers. There must be an edge. Computational boundaries. In fact, if we're in a simulation, we can derive what the edge would be like. A simulation has to run on hardware. That hardware has finite memory and finite processing power. Therefore, the simulation can't be infinitely detailed in all directions simultaneously. The observable universe. This might be the area the simulators are actively computing. Everything outside our current observable universe might not be computed in detail. It might be computed on demand, only when we look at it. Or it might not be computed at all. This is actually similar to how video games work. Video game worlds aren't fully detailed in areas the player can't see. The game only renders in detail the areas the player is looking at. Everything else is either simplified, procedurally generated, or not computed at all. Could the universe work the same way? Could regions of space we're not observing be uncomputed or lightly computed? Could the act of observation trigger detailed computation? If so, this would be testable. We could look for places where detailed observation reveals unexpected simplicity, or where different observers see different things in the same location. The horizon problem. Cosmologists have long puzzled over the horizon problem. How is the universe so uniform in all directions when different regions shouldn't have been in contact? One explanation. If the universe is simulated, the simulators might set it up to be uniform everywhere, not just in the parts we can observe. They could enforce cosmic uniformity as a computational shortcut. The nature of the boundary. If there is an edge, what's its nature? A hard boundary. Space-time simply ends. You can't go further. The laws of physics might break down or become ill-defined at the boundary. A soft boundary. Space-time curves back on itself before the boundary, so you never actually reach it. The universe is finite, but you're trapped inside by geometry, not by a wall. A reflective boundary. You reach the edge and bounce back like a particle in a box. Waves could reflect off the boundary, creating interference patterns we might observe. A computational boundary. The simulation becomes less detailed at the edges. Reality becomes fuzzier, less well-defined. Causality breaks down. Simulation, hypothesis, implication. Here's where this gets interesting for the simulation hypothesis. If we're in a simulation, the simulators have to make a choice about the universe's geometry. They could make it infinite, which is computationally expensive, or they could make it finite, which is more efficient. If they make it finite, where is the boundary? Is it hidden? Is it designed in such a way that conscious beings can never reach it? Or maybe they tell us about it. Maybe the simulators deliberately put hints about the universe's boundary in the physics so that eventually we figure it out. Or maybe the boundary is right there and we just don't recognize it. Maybe what we think is the infinite universe is actually a finite simulation with carefully designed boundary conditions that make it seem infinite. What astronomers are looking for? There are actually searches for evidence of an edge or boundary, topology of the universe. Astronomers measure the geometry of space-time. If the universe is finite and topology looped back on itself, we might see repetitions in the cosmic microwave background, the same galaxy or structure appearing in multiple places due to light traveling around the edge multiple times. Some researchers have claimed to find evidence of such repetitions, though it's controversial and not widely accepted. Acceleration of cosmic expansion. The expansion of the universe is accelerating, driven by dark energy, but the acceleration isn't uniform. Some regions expand faster than others. Could this be a sign of boundary effects? Could the universe be expanding differently near its edges? Gravitational wave patterns. Gravitational waves from merging black holes travel across the universe. If there were boundaries, these waves might reflect or refract, creating patterns we could detect. Let me try to bring this all together and make an honest assessment. The case for simulation fine-tuning. The constants of physics fall within an improbably narrow range. Simulation explains this without requiring infinite universes. Quantum weirdness. Quantum mechanics seems computational. Superposition, entanglement, and wave function collapse all look like features of a computing process. Mathematical structure. The universe is described perfectly by mathematics. Too perfectly. Why should an uncaused fundamental universe conform to human mathematics so precisely? Information. Density. The holographic principle suggests reality is fundamentally informational. Information is what computers process. Error-correcting codes. James Gates found error-correcting codes in string theory equations. These are computational artifacts. Cosmic ray signatures. The GZK cutoff might indicate lattice structure. Other cosmic ray patterns might reveal computational discretization. Consciousness. The fundamental mystery of consciousness, why we experience anything at all, is unexplained in physicalism. Maybe consciousness is what the simulation is fundamentally about. Observer effect. Observation affects reality. This is true in quantum mechanics and might suggest consciousness plays a computational role. Logical consistency. The simulation argument is logically airtight. Either civilizations go extinct, avoid simulation, or we're in one. At least one must be true. Explanatory power. The simulation hypothesis explains many seemingly unrelated phenomena under one framework. The case against simulation. Unfalsifiability. The hypothesis is hard to falsify. Any observation can be reinterpreted as evidence of simulation. This makes it not science. Occam's razor. The simulation hypothesis adds layers of complexity. Simulators, their universe's simulators. Simpler to assume the universe is fundamental. No positive evidence. We have no definitive proof. All the evidence we discussed is circumstantial and open to alternative interpretation. Infinite regress problem. If we're in a simulation, the simulators are in a universe. If that's simulated, what about their simulators? This leads to infinite regress, which doesn't solve anything. Difference collapse. If a simulated universe follows all the same laws as a base reality, what's the meaningful difference? The distinction becomes philosophically empty. Resources problem. Creating a simulation detailed enough to include conscious beings would require impossibly vast computational resources. Where would the simulators get such resources? Measurement problem. The fine-tuning we observe might be explained by multiverse theory or anthropic selection. We don't need simulation. Consciousness problem. Consciousness might be an emergent property of physical systems, not something that requires simulation or computation. Alternative explanations. For every piece of evidence, there's an alternative explanation that doesn't require simulation. Pragmatic irrelevance. Even if true, the simulation hypothesis doesn't change how we should live our lives or do science. My assessment. Honestly, I think the evidence is mixed. The fine-tuning problem is real and serious. The simulation hypothesis is one good explanation for it, but not the only one. The multiverse is another. Anthropic selection is another. The mathematical structure of the universe is mysterious and beautiful, but it could reflect the nature of reality rather than indicating simulation. The simulation argument is logically sound, but it's not empirical evidence. It's a philosophical argument about probability. The cosmic ray signatures and error-correcting codes are interesting, but they're not definitive. They're hints at most. What I'm convinced of is this. The question is not scientifically closed. We don't have proof either way. And it's worth taking seriously. After all of this, all the evidence, all the arguments, all the philosophical considerations, what should we conclude? I think we should conclude that we don't know. And that's okay. The value of uncertainty. There's something important about living with questions unanswered. It keeps us humble. It keeps us curious. It prevents us from becoming dogmatic. The greatest scientists are often those most comfortable with uncertainty. Einstein didn't believe quantum mechanics was the final word because he couldn't accept the probabilistic nature of reality. He wanted a deeper deterministic layer. He was wrong about that, but his discomfort with uncertainty pushed physics forward. Similarly, discomfort with the question, are we in a simulation, might push us toward deeper understanding of reality. The practical implications. But even if we don't know whether we're in a simulation, some practical implications follow. Consciousness matters. Whether we're in simulation or not, consciousness is real. Your experience is real. This should inform how we treat each other, how we design AI systems, how we think about suffering and joy. Information is fundamental. The simulation hypothesis takes seriously the idea that information, not just matter, is fundamental. This might drive research in quantum information theory, computational physics, and the nature of meaning. Humility about reality. We should recognize that our understanding of reality is limited. We see through a glass darkly. There might be vast domains of reality we don't understand or can't perceive. Value creation. If the universe is impersonal and meaningless, whether simulated or fundamental, then meaning is something we have to create. This is actually empowering. It means we're not passive observers. We're active creators of meaning. The question that remains, the deepest question remains, why is there something rather than nothing? Whether the something is a base reality or a simulation doesn't change the profundity of this question. Why does anything exist? Why is there computation happening? Why is there consciousness? I don't know, and I don't think anyone does. But the fact that we can ask this question, that we can wonder about the nature of reality, that we can use logic and mathematics and observation to investigate the universe, this is extraordinary. Whether we're in a simulation or not, we're conscious. We're here. We're able to understand some aspects of the universe around us, and that's remarkable. Where this leaves us, we've gone from quantum mechanics to cosmic rays to consciousness to the nature of meaning itself. Let me try to synthesize what we've covered and where it points. The big picture. We live in a universe that has laws of physics that are improbably fine-tuned for life, behaves in ways that seem deeply computational at the quantum level, is described by mathematics with almost supernatural accuracy, contains consciousness, which we don't fully understand, might be infinite or might be finite with hidden boundaries, will eventually reach a state where consciousness cannot exist. And we're asking, is this universe fundamental? Or is it a simulation? The evidence is suggestive but not conclusive. The arguments are interesting but not decisive. We genuinely don't know. But here's what strikes me. The question itself is revealing. The fact that we can ask it, the fact that it's not obviously absurd, the fact that serious physicists take it seriously, the fact that it points to real puzzles in our understanding of reality, all of this suggests something important. The simulation hypothesis, whether true or false, reveals something about the nature of our universe. Our universe is computational in its deep structure. This isn't a fringe belief anymore, it's mainstream physics. Quantum mechanics is fundamentally about information. Black holes encode information on their surfaces. Space and time might emerge from entanglement. Consciousness is stranger than we thought. We still don't understand why consciousness exists. We don't understand the hard problem of consciousness, why we experience anything at all. The simulation hypothesis is one way to think about this, but it points to a genuine mystery. Reality is more layered than we assumed. Whether or not we're in a simulation, it seems there are levels to reality, layers of emergence, the quantum level, the classical level, the conscious level, the social level. These aren't just different descriptions of the same thing. They seem to have genuine existence. Meaning is created, not found. If the universe is a simulation, meaning comes from the intention of the creators and our own choices. If it's fundamental, meaning still comes from our choices and our consciousness. Either way, meaning isn't handed to us. We have to create it. The paradox of the question. Here's something interesting. Asking whether we're in a simulation might be self-refuting. If we're in a simulation sophisticated enough that we can ask this question, conscious enough to wonder about our own nature, then we've already achieved something remarkable. We've created, or the simulators have created, conscious beings capable of self-reflection and questioning. That's the whole point of a simulation, not to create a universe and leave it alone, but to create beings who can wonder, who can question, who can grow and change and discover. So the fact that we're asking this question is itself evidence that we're in a sophisticated simulation. or it's evidence that consciousness in any substrate naturally evolves to question itself. Either way, the question matters. If I could go back and talk to myself before I started thinking deeply about this, I'd say, you're going to spend a lot of time on this question. You're going to read physics papers and philosophical arguments. You're going to think about consciousness and reality and meaning, and you're going to come to some conclusions. First, you won't find definitive proof either way. That's okay. Some questions don't have final answers, and that's where the interesting thinking happens. Second, you'll realize that the simulation hypothesis isn't really about whether we're in a simulation. It's about understanding what consciousness is, what reality is made of, and what makes life meaningful. Third, you'll find that taking the question seriously changes how you see the world. It makes you more humble about your understanding. It makes you more appreciative of consciousness, yours and others. It makes you take seriously the responsibility we have to think carefully about what we create. Fourth, whether or not we're in a simulation, your life has meaning. Your consciousness is real. Your experiences matter. The people around you matter. And how you treat them, how you create meaning, how you contribute to the world, that's what's important. Fifth, you'll come to see that the simulation hypothesis and traditional religious frameworks are asking similar questions. Both are trying to explain fine-tuning. Both are trying to understand consciousness. Both are trying to give meaning to existence. The difference is just in the language and the specific claims, and maybe that convergence is important. Maybe it suggests we're asking the right questions, even if we don't have the right answers yet. Sixth, you'll realize that the best response to uncertainty is curiosity, not fear. Don't be afraid that we might be in a simulation. Be excited that there are still mysteries to explore. Be grateful that consciousness exists and that you get to participate in trying to understand it. The ultimate mystery. After all this investigation, after all these arguments and evidence and counter-arguments, we're left with the ultimate mystery. Why is there something rather than nothing? And I don't think this question has an answer. Not a final one, not a satisfying one. A simulation needs a simulator. But a simulator exists in another universe, which might be a simulation, which needs a simulator, and so on. A fundamental universe needs an explanation for its initial conditions, but any explanation just pushes the question back further. The mathematical structure of reality is remarkable. But why does mathematics exist? Why do these particular mathematical structures? Why is there anything for the math to describe? I think this question, why is there something rather than nothing, might be fundamentally unanswerable. Not because we're not smart enough yet, but because any answer we could give would require something that itself needs explanation. It's infinite regress all the way down. And I've come to think that's okay. That's what makes life interesting. That's what keeps us searching. The beauty of not knowing. Here's the thing I want to emphasize most strongly. Not knowing is not a failure. It's the starting point for discovery. We don't know if we're in a simulation. We don't know the ultimate nature of consciousness. We don't know why there's something rather than nothing. We don't know what happens after we die. We don't know if we're the only consciousness in the universe or if there are infinite others. And these unknowns are beautiful. They're the frontier. They're what drives science and philosophy and art and music. They're what make being conscious interesting. If we knew everything, what would be left to discover? If the universe were fully explained, where would wonder come from? The simulation hypothesis is valuable precisely because it's uncertain. It keeps us thinking. It keeps us humble. It keeps us open to possibilities. Let me leave you with one more thought experiment. Imagine you discover absolute proof that we're in a simulation. Definitive, irrefutable proof. You find the code, you find the simulators, you know for certain. What changes? I think the answer is not as much as you'd think. You'd still be conscious. The sunset would still be beautiful. Love would still matter. Friendship would still be valuable. Your experiences would still be real. The only thing that would change is your understanding of what you are. You'd know you're a computational process, but you'd still be you. And then imagine the opposite. Imagine you discover absolute proof that we're not in a simulation, that this is base reality, that nothing is computing us. We're just fundamental particles in a fundamental universe. What changes then? Again, I think not that much. You're still conscious. The sunset is still beautiful. Love still matters. Your experiences are still real. The only thing that changes is your understanding of the origin of the universe. But your life doesn't change. This suggests to me that the simulation hypothesis, while intellectually fascinating, isn't the most important question after all. The most important question is, how do we live? How do we treat each other? How do we create meaning? How do we reduce suffering? How do we understand consciousness and what makes life valuable? Those questions matter whether or not we're in a simulation. We've explored evidence in science and philosophy and thought experiments. We've looked at what physicists say and what the logical arguments suggest. And we've arrived at a simple conclusion. We don't know, and that's okay. The simulation hypothesis is interesting because it forces us to think carefully about the nature of reality, consciousness, and meaning. It's not interesting because it's probably true. What matters is that we keep asking questions, that we stay curious, that we remain humble about what we don't know, that we value consciousness and meaning and connection. Whether this is base reality or a simulation, you're here. You're conscious. You're real in the way that matters most, in your own subjective experience. And that's enough to build a meaningful life on. Let me dive into some lesser-known scientific observations and theoretical findings that connect to simulation theory in interesting ways. The quantum Zeno effect. What it is. The quantum Zeno effect is a weird phenomenon in quantum mechanics. It says that if you measure a quantum system frequently enough, you can prevent it from changing state. Imagine an unstable particle that would normally decay. If you measure it constantly, checking, is it still there? The particle won't decay. The very act of observation freezes the particle in place. It's named after Zeno's paradox. The ancient Greek thought experiment about an arrow in flight that's always frozen at each instant. Most people have heard of the observer effect in quantum mechanics, the idea that observation affects reality, but few people know about the Zeno effect specifically, which is a much more dramatic version of this principle. Connection to simulation. If we're in a simulation, the quantum Zeno effect makes sense. The simulation only needs to compute what's being observed. When you're not looking at something, it doesn't need to be fully computed. But when you measure it, when you observe it, the simulation has to commit to a specific state. This is exactly how the Zeno effect works. Constant measurement forces the system into a definite state. What if the entire universe works this way? What if particles only have definite properties when measured, and the rest of the time they exist in superposition because those unobserved regions don't need to be fully computed? This would be a computationally efficient design. The simulators only compute what conscious observers are looking at. The axis of evil. What it is. When astronomers measure the cosmic microwave background, the radiation left over from the Big Bang, they find that it's almost perfectly uniform in all directions. This uniformity is expected and is one of the best confirmations of the Big Bang theory. But in 2005, astronomers Kate Land and João Magejo discovered something strange. The universe isn't quite as uniform as it should be. There's a preferred direction in space. They found that when they looked at temperature variations in the CMB, those variations seemed to align with the plane of our solar system. This was shocking because there shouldn't be any preferred direction. The universe should look the same in all directions. They called this the axis of evil, partly as a joke, partly because it violated the cosmological principle, the assumption that the universe is isotropic and homogeneous. Most people don't know about the axis of evil because it's still debated whether it's real or a statistical artifact. It challenges fundamental assumptions in cosmology. Mainstream cosmologists have been skeptical, but the evidence kept accumulating. Other researchers found similar alignments in other datasets, in gamma-ray bursts, in quasar distributions, in supernova distributions. All seemed to align with the same axis. Connection to simulation. If the universe is simulated, why would there be a preferred direction? One possibility: the simulators left a signature. The axis of evil could be evidence that the simulation was created from a particular orientation, like a fingerprint built into the code. Another possibility: computational efficiency. Simulations often have a preferred coordinate system. If the simulators organize space-time along certain axes, there might be subtle signatures of that organization in the data. Or, more speculatively, the axis of evil might point toward the location of the simulator's computers, or toward the camera angle from which they're observing us. This is highly speculative, but it's a real anomaly in the data that we don't fully understand: parity violation and the handedness of matter, what it is. In the 1950s, physicists Tsung-Dao Lee and Chen-Ning Yang discovered something shocking. The weak nuclear force violates parity symmetry. Parity symmetry is the idea that the laws of physics should be the same whether you're looking at something or looking at its mirror image. If you flip the universe horizontally, the laws should remain the same. But they don't. The weak force, responsible for radioactive decay, treats left-handed particles differently from right-handed particles. This is strange because there's no obvious reason why the universe would prefer left over right. It seems arbitrary. Even stranger, all organic molecules on Earth are left-handed. All amino acids, the building blocks of proteins, are left-handed. All sugars are right-handed. This asymmetry is called homochirality. Why? We don't know. It could be random. It could be because life on Earth happened to start with left-handed amino acids, and then everything else evolved to be compatible with that. But we don't have a deep understanding. Most people don't know about parity violation because it's taught in advanced physics courses and doesn't affect everyday life. But it's fundamental to how the universe works. Connection to simulation. If the universe were truly symmetric and fundamental, why would there be parity violation? Why would the weak force treat left and right differently? One answer: it's just a feature of our universe. No explanation needed. But another answer: the simulators chose to break parity symmetry, maybe to make the simulation more interesting, maybe to give it structure, maybe as a design choice. And the homochirality of life on Earth, that could be a signature. The simulators could have engineered life to have a specific handedness, as a way of showing that life is designed, not random. Or it could be that the simulators, in whatever universe they come from, also have parity violation. Life there is also left-handed. And when they created this simulation, they copied that feature. The proton radius puzzle. What it is for decades, physicists measured the radius of a proton and got consistent results. Then in 2010, a new measurement technique gave a different answer. The proton appeared to be smaller than previously thought. This shouldn't matter much. It's a small discrepancy. But it was puzzling because different measurement techniques should converge on the same answer. Then, in 2019, new measurements suggested the proton was actually even smaller. Then, in 2021, measurements swung back toward the larger radius. We still don't know which is correct. The proton's radius remains uncertain. Most people don't know about the proton radius puzzle because it's a technical issue in atomic physics. It doesn't grab headlines. But physicists find it deeply puzzling because it suggests there might be something wrong with our understanding of quantum electrodynamics, one of the most precisely tested theories in science. Connection to simulation. If the universe is being simulated on discrete computers, there might be rounding errors or precision limits. When we measure the proton radius with extreme precision, are we hitting the limits of the simulation's precision? Are we seeing computational artifacts? The fact that different measurement techniques give different results could suggest that the simulation handles measurements differently depending on how you measure. This is speculative, but it points to an interesting principle. If a simulation is running at finite precision, we should expect to find measurements that don't quite line up. The Pioneer anomaly. What it is. In 1980, astronomers noticed something odd. The Pioneer 10 and Pioneer 11 spacecraft, launched in the 1970s to explore the outer solar system, were experiencing an unexplained deceleration. As they traveled away from the sun, they were slowing down more than expected. Something was pulling them back. The anomaly was tiny, about 8 nanometers per second squared. Over years, it added up. The spacecraft were about 400,000 kilometers off where they should have been. Physicists proposed wild explanations: undetected dust clouds, dark matter, modifications to gravity, new particles. Some suggested it was a sign that Einstein was wrong and we needed a new theory of gravity. Then in 2012, a detailed analysis showed the anomaly was likely due to heat from the spacecraft's instruments. The spacecraft were radiating heat asymmetrically, creating a tiny thrust. The mystery was solved. It wasn't a fundamental physics discovery. The Pioneer anomaly is obscure because once it was solved, it dropped out of the news. People don't remember it. But for several decades, it was a genuine mystery at the edge of physics. Connection to simulation. The Pioneer anomaly is interesting for simulation theory, not because it's necessarily evidence of simulation, but because it illustrates a principle. Anomalies happen. Unexplained things show up, and when we investigate them carefully, sometimes they have mundane explanations, and sometimes they point to deeper truths. If we're in a simulation, there might be anomalies, places where the simulation doesn't quite work as expected, places where the code has bugs, places where the simulators made shortcuts. The Pioneer anomaly could have been that, but it turned out not to be. This teaches us to be careful. Extraordinary claims require extraordinary evidence, but it also shows we should keep looking for anomalies because some of them might point to something real. The Wilkinson Microwave Anisotropy Probe, cold spot. What it is. The cosmic microwave background is almost perfectly uniform with tiny variations in temperature. These variations are crucial for understanding the early universe. They show where matter clumped together to form galaxies. But in 2004, astronomers discovered a region of the CMB that was unexpectedly cold, much colder than the surrounding regions. It's about 1.7 degrees across in the sky, about 3 times the size of the full moon. This region, called the WMAP cold spot, shouldn't exist. The CMB variation should be random and distributed evenly. A spot this large and this cold is statistically improbable. Why? It's obscure. Most people don't know about the cold spot because CMB observations are technical and don't make headlines. But cosmologists find it puzzling. Possible explanations. Scientists have proposed several explanations. Statistical fluctuation. With enough data, you're bound to find some unusual patterns by chance. This might just be a lucky cluster. Gravitational lensing. The light from the CMB could have been bent by massive structures on its way to us, creating a cold spot. Local void. There might be a region of space with fewer galaxies nearby. This region could absorb photons, making that part of the sky appear colder. Exotic physics. Maybe the spot is a signature of something exotic, a collision with another universe, a cosmic string, or some other phenomenon. Connection to simulation. The WMAP cold spot is interesting for simulation theory because it's an anomaly, something that shouldn't be there. If we're in a simulation, anomalies might be bugs in the code, deliberate signatures left by the simulator's regions where the simulation's resolution is lower, places where the simulator's render distance reaches its limit. The cold spot could be evidence of any of these, or it could just be a statistical anomaly. But it keeps us thinking about what unexpected features in the universe might mean. The lithium-7 problem. What it is. When the universe was very young, about 3 minutes after the Big Bang, nuclear fusion created the first atomic nuclei. This process created helium, deuterium, heavy hydrogen, and lithium. Physicists can calculate exactly how much of each element should have been created based on the physics of the early universe. When they compare these predictions to observations of old stars, most of the numbers match beautifully. It's one of the great triumphs of Big Bang cosmology. But lithium-7 doesn't match. We observe about 3 to 4 times less lithium-7 in old stars than the theory predicts. This is called the lithium problem, or the lithium-7 problem. Most people don't know about this because nuclear cosmology is a technical field. But physicists find it deeply troubling because it suggests something is wrong with either our understanding of the early universe, our measurements of lithium in old stars, our nuclear physics. Possible explanations measurement. Error. Maybe we're measuring lithium wrong in old stars. Destruction. Maybe lithium-7 is destroyed by processes in stars that we don't fully understand. New physics. Maybe there's physics in the early universe we don't know about that affects lithium production. Connection to simulation. The lithium-7 problem is interesting for simulation theory because it's a fundamental inconsistency in our understanding. If the universe is a simulation, inconsistencies might point to approximations the simulators made to save computational resources, areas where the simulators haven't fully implemented the physics bugs. The simulators might have simplified nuclear physics in certain regimes to save computation. Lithium-7 production in the early universe might be one of those simplified areas. The mismatch between theory and observation could be evidence of this simplification. The flyby anomaly. What it is. When spacecraft perform gravitational flybys around planets using the planet's gravity to speed up or slow down, they should gain or lose energy in precisely calculated amounts. But starting in the 1990s, astronomers noticed that some spacecraft were gaining or losing slightly more energy than expected. The Near spacecraft, after a flyby of Earth in 1998, was traveling about 13 millimeters per second faster than predicted. The Cassini spacecraft, after a flyby in 1999, was off by about 0.2 millimeters per second. These are tiny discrepancies, but they're consistent. Something is wrong with our understanding of gravity, or the measurements, or something else. The flyby anomaly is obscure because it's a technical issue that only affects spacecraft navigation, but it's also mysterious because we don't know the cause. Some physicists have proposed exotic explanations, modifications to general relativity, dark matter interactions, or something else, but no consensus has emerged. Connection to simulation. The flyby anomaly is interesting because it suggests there might be small, consistent errors in how the universe behaves. Errors that don't show up in most experiments but emerge in specific, precise conditions. If we're in a simulation, such errors might indicate precision limits in how the simulators calculate gravitational interactions, different computational methods for different types of interactions, accumulated rounding errors in specific scenarios. The fact that the errors are small but consistent suggests not random noise, but systematic effects. This is the kind of thing you'd see in a simulation with finite precision or specific computational shortcuts. The axis alignment of galaxies. What it is galaxies spin. They have angular momentum. If the universe is truly random and isotropic, the same in all directions, the spin axes of galaxies should point in random directions. But they don't. Multiple studies have found that the spin axes of galaxies seem to align with structures in the universe. Galaxies in the same cosmic web tend to spin in similar directions, or their spins tend to align with the filaments of the cosmic web structure. This is called angular momentum alignment or spin alignment. Most people don't know about galaxy spin alignment because galactic dynamics is a specialized field, but it's important because it suggests the universe has structure and organization at large scales that we don't fully understand. Possible explanations. Tidal forces. The universe's matter distribution creates tidal forces that align galaxy spins over time. Initial conditions. Maybe the universe started with aligned spins due to how density perturbations collapsed in the early universe. Systematic measurement error. Maybe we're biased in how we measure galaxy spins. Connection to simulation. Galaxy spin alignment is interesting because it shows unexpected order in a supposedly random universe. If the universe is a simulation, this order could mean the simulators created structure rather than pure randomness. There are organizing principles built into the simulation. The simulation has a preferred direction or axis, like the axis of evil, or it could just be physics. Tidal forces can produce alignment without any special design, but it's the kind of feature that, in a simulation, would be an intentional design choice to create an interesting structured universe. The quantized redshift hypothesis. What it is. When astronomers measure the redshift of distant galaxies, how much their light is shifted toward red due to the expansion of the universe, they notice something odd. The redshifts don't appear to be continuous. They seem to cluster at certain values. In the 1970s, astronomer William Tift proposed that galaxy redshifts are quantized. They come in discrete steps rather than varying continuously. This was controversial. Most physicists rejected it because redshift should be continuous according to general relativity. But Tift accumulated evidence that the quantization was real. The quantized redshift hypothesis is obscure because most astronomers don't believe in it. It contradicts general relativity. It's been criticized on methodological grounds. But Tift wasn't an eccentric crank. He was a serious astronomer who worked at the Lowell Observatory, and his data was real. It's just been interpreted differently by others. Some astronomers have found evidence supporting quantization. Others have shown the apparent quantization is a statistical artifact. The debate continues. Connection to simulation. If the universe is a simulation running on discrete computers, quantization makes sense. Reality, at the finest scale, would be discrete, not continuous. Quantized redshifts would be a signature of this discreteness. They'd be evidence that space-time itself is quantized at some level, that the universe has a fundamental grid size. This connects back to the idea of the lattice universe. If the universe is computed on a lattice, we'd expect to find quantization effects. Quantized redshifts could be exactly that. The Casimir effect. What it is. The Casimir effect is one of the strangest phenomena in physics. In quantum mechanics, empty space isn't actually empty. The vacuum is filled with virtual particles constantly popping in and out of existence. This is allowed by the uncertainty principle. You can create a particle and its antiparticle for a brief instant. In the 1940s, Dutch physicist Hendrik Casimir realized that if you place two uncharged metal plates very close together, they would affect this quantum vacuum. The virtual particles between the plates would be restricted. Only certain wavelengths could exist in the narrow gap. Outside the plates, more wavelengths are possible. This difference in available wavelengths creates a pressure. The plates are pushed together. Attractive force from nothing. The Casimir effect has been experimentally verified multiple times. It's real. Most people don't know about the Casimir effect because quantum field theory is advanced and the effect is subtle. But it's one of the most profound phenomena in physics because it shows that empty space isn't empty. Virtual particles have real effects. We can extract energy from the vacuum connection to simulation. The Casimir effect is profound for simulation theory because it suggests the quantum vacuum, empty space, is computational. The virtual particles are computation happening. The vacuum is alive with activity. The universe is constantly calculating, even in empty space. If we're in a simulation, this makes perfect sense. Every piece of space is being computed. Every instant, the simulation is calculating quantum fluctuations, virtual particles, vacuum effects. The Casimir effect is evidence that reality, at the most fundamental level, is computational activity. Hawking radiation and black hole. Thermodynamics. What it is in 1974, Stephen Hawking made a shocking prediction. Black holes aren't completely black. They emit radiation. The mechanism is subtle. Near the event horizon of a black hole, quantum fluctuations can produce pairs of virtual particles. Sometimes one particle falls into the black hole while the other escapes. From far away, it looks like the black hole is emitting particles. This is Hawking radiation. Hawking also showed that black holes have thermodynamic properties. They have temperature, entropy, and can lose energy. As a black hole radiates away its mass, it gets smaller and hotter, radiating faster until eventually it explodes in a final burst of energy. Hawking radiation hasn't been directly observed. Black holes don't emit enough radiation for us to detect. But it's profound because it connects thermodynamics, quantum mechanics, and general relativity. Connection to simulation. Hawking radiation is profound for simulation theory because it suggests that information might be encoded at event horizons. In fact, the discovery of Hawking radiation led directly to the holographic principle, the idea that all the information in a volume of space is encoded on its boundary, at the event horizon of a black hole, or at the cosmological horizon of the universe. If the holographic principle is correct, then the universe is fundamentally a projection from a lower dimensional boundary, which is, in a sense, a simulation where the real computation happens on a 2D surface and the 3D world is a projection. This suggests that simulation isn't a fringe idea. It's built into the mathematics of modern physics. The charge asymmetry problem. What it is. In the early universe, particles and antiparticles should have been created in equal amounts. They should have annihilated each other completely, but they didn't. We exist. That means there was slightly more matter than antimatter in the early universe. The asymmetry is tiny, about 1 extra matter particle for every 10 billion matter-antimatter pairs, but it's enough to account for all the matter in the universe today. Why is there this asymmetry? We don't know. It's called the baryon asymmetry, or CP violation problem. Most people don't know about the charge asymmetry problem because particle physics is technical, but physicists find it deeply puzzling because it's one of the biggest open questions in physics. Possible explanations. Sakharov conditions. In the early universe, certain conditions might have favored matter over antimatter. Neutrino physics. Asymmetries in neutrino interactions might be responsible. New particles. There might be particles we haven't discovered yet that cause the asymmetry. Leptogenesis, asymmetries in the lepton sector, electrons, neutrinos, might be converted to baryon asymmetry. Connection to simulation. The charge asymmetry is interesting for simulation theory because it's a feature of the universe that seems arbitrary and fine-tuned. If the universe were random, you'd expect matter and antimatter to be equal. But they're not. Why? One answer, it's just how the universe is. No deeper explanation. Another answer, the simulators set it up this way. They chose to break the symmetry to create a universe with matter. This might have been intentional to make the simulation interesting, to create complex structures. Or the asymmetry might be a necessary feature of any simulation. The simulator's universe might also have matter-antimatter asymmetry. When they created this simulation, they copied that feature. Planck scale physics and quantum foam. What it is. At extremely small scales, the Planck scale, about 10 to the power of minus 35 meters, quantum effects become so extreme that space-time itself might break down. We can't directly observe these scales. They're far too small, but theoretically at the Planck scale, space might become foamy, filled with tiny black holes and quantum fluctuations that constantly appear and disappear. This is called quantum foam. If quantum foam is real, space-time wouldn't be smooth. It would be granular with a minimum size scale, the Planck length. Planck scale physics is obscure because we have no experimental access to it. It's purely theoretical, but it's important because it represents our best guess about the structure of space and time at the most fundamental level. Connection to simulation quantum foam is directly relevant to the simulation hypothesis because it suggests space-time has a discrete, granular structure. If the universe is a simulation, it would naturally be discrete at some fundamental level. The Planck scale might be the resolution of the simulation. Space and time might be pixels in the cosmic simulation. The graininess of quantum foam might be evidence of this pixelation. consciousness, and the quantum measurement problem. What it is, in quantum mechanics, particles exist in superposition, multiple states simultaneously until they're measured. Then they collapse into a definite state. But what counts as a measurement? Does it require a conscious observer? Or is it any interaction with the environment? This is called the measurement problem. And physics still doesn't have a consensus answer. Some interpretations of quantum mechanics require consciousness. The von Neumann-Wigner interpretation explicitly states that consciousness causes wave function collapse. Other interpretations, like many worlds, say there's no collapse. The superposition branches into multiple realities. Most physicists learn quantum mechanics without deeply engaging with the measurement problem. It's treated as a philosophical issue, not a physics problem. But it's fundamental. What is the relationship between consciousness and physical reality? Connection to simulation. The measurement problem is crucial for simulation theory because it suggests consciousness is fundamental to physics. If consciousness causes wave function collapse, then consciousness is woven into the fabric of reality. Consciousness isn't an emergent property, it's a basic feature like mass or charge. In a simulation, this makes sense. The simulation might be fundamentally designed around conscious observation. The simulators might be conscious beings, and the simulation might exist primarily for them to observe or for consciousness within the simulation to develop. The measurement problem might be pointing to this, that consciousness and physical reality are deeply intertwined. That observation literally creates reality, that the universe is participatory. The delayed choice, quantum eraser experiment. What it is. The delayed choice quantum eraser is one of the strangest experiments in quantum mechanics. Here's how it works. You send photons through a double slit. Normally, each photon goes through both slits, quantum superposition, and creates an interference pattern on a screen. But you can mark which slit the photon goes through using detectors. If you do this, the interference pattern disappears. The photons act like particles, not waves. Here's the weird part. You can then use a special device to erase the information about which slit the photon went through. And when you do this, even if it happens after the photon has already hit the screen, the interference pattern comes back. The act of erasing information in the future affects what happened in the past. Most people have heard of quantum mechanics being weird and observation mattering, but the delayed choice quantum eraser shows that the weirdness goes even deeper. The past and future are connected through information. Connection to simulation. The delayed choice quantum eraser suggests that causality isn't what we think it is. The future can influence the past through information. In a simulation, this makes perfect sense. The simulation isn't computing one moment at a time in a linear sequence. Instead, the entire space-time might be computed at once, with information propagating both forward and backward in time. The experiment shows that quantum mechanics is retrocausal. The future can determine the past. This is exactly what you'd expect in a simulation where the entire universe is computed at once. The uncertainty principle and information. What it is. Heisenberg's uncertainty principle states that you can't simultaneously know both the position and momentum of a particle with arbitrary precision. The more precisely you know position, the less precisely you know momentum, and vice versa. This isn't a limitation of our measurement instruments. It's fundamental to quantum mechanics. It reflects something deep about the nature of reality. But here's something subtle. The uncertainty principle is directly related to information theory. If you have only a limited amount of information about a system, you can't specify both position and momentum precisely. You have to trade off between them. The uncertainty principle is a statement about how much information nature allows you to have about a quantum system. Most people know about uncertainty from popular science, but few realize it's fundamentally about information, not about measurement difficulty. Connection to simulation. The uncertainty principle, as an information principle, directly supports the simulation hypothesis. In a simulation, information is the fundamental substrate. The uncertainty principle might be built in to limit how much information the simulators need to store. Instead of specifying both position and momentum for every particle, which would require double the information, the simulation only specifies one or the other, depending on what's being measured. This is computationally efficient. The uncertainty principle might be a feature designed to reduce the computational load. The fine structure, constant mystery. What it is? The fine structure constant is a dimensionless number that appears throughout physics. It's approximately 1 over 137. This number determines the strength of the electromagnetic force. It appears in quantum electrodynamics, in atomic physics, in chemistry. Why is it exactly what it is? We don't know. It seems arbitrary. Richard Feynman called it one of the greatest damn mysteries of physics. Over the decades, physicists have proposed wild explanations. Maybe it's related to the number of particles in the universe. Maybe it's determined by string theory. Maybe it's not constant and changes over time. Some have even proposed it might be exactly 1/137th as a mathematical fact, or that it might be related to the geometry of the universe. Why it's obscure. Most physicists treat the fine structure constant as a given, a measured value we use in equations. But philosophically, it's mysterious. Why this value? Why not 100th or 1/200th? Connection to simulation. The fine structure constant is a parameter in the simulation. The simulators chose this value when they set up the physics. Why this particular value? Maybe because it's aesthetically pleasing. 1 over 137 is prime. It allows for stable atoms and chemistry. It's a signature or message from the simulators. Some people have speculated that the fine structure constant contains hidden information, that if you look at its digits carefully, you can find a message or pattern. This is probably not true, but it shows how mysterious this number seems. It feels like it should mean something. Quantum entanglement and non-locality. What it is. Quantum entanglement is when two particles become correlated in such a way that measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance, and initially thought it meant quantum mechanics was incomplete. But decades of experiments have confirmed that entanglement is real. Particles really can be instantaneously correlated across arbitrarily large distances. This seems to violate locality, the principle that nothing can travel faster than light. But it doesn't quite violate it, because you can't use entanglement to send information faster than light. The correlations only become apparent when you compare measurements, which requires classical communication. Most people have heard of quantum entanglement, but few understand how profound it is. Entanglement suggests that distant parts of the universe are fundamentally connected, not through any signal passing between them, but through a deeper structure of reality. Connection to simulation. Entanglement is striking evidence for the holographic principle and simulation hypothesis. In a simulation, entanglement makes sense. Entangled particles aren't really separate. They're different representations of the same underlying information in the simulation. When you measure one particle, you're accessing certain information. When you measure the entangled partner, you're accessing related information. They're correlated not because something travels between them, but because they're computed together. In fact, some physicists have proposed that entanglement is evidence that space-time is emergent, that space itself emerges from entanglement patterns. If space emerges from entanglement, then space isn't fundamental. What's fundamental is information and correlations, which is exactly what a simulation would be: pure information and computation. The arrow of time problem. What it is: the laws of physics are time symmetric. If you reverse the direction of time in Maxwell's equations, Schrödinger's equation, or Einstein's field equations, they still work. Yet our universe has a clear arrow of time. The past is different from the future. Entropy increases. You can't unscramble an egg. Why? The answer is usually given as entropy. The second law of thermodynamics says entropy always increases. This creates a direction to time. But here's the puzzle. If the fundamental laws are time symmetric, why does entropy increase? Where does this asymmetry come from? Some physicists have proposed that the arrow of time is related to the initial conditions of the universe. The universe started in a low entropy state, the Big Bang, and entropy has been increasing ever since. But this just pushes the question back. Why did the universe start in a low entropy state? Most people take the arrow of time for granted. It seems obvious that the future is different from the past. But physicists realize this is actually mysterious. The universe's asymmetry in time isn't explained by the fundamental laws. It has to come from initial conditions. Connection to simulation. The arrow of time is interesting for simulation theory because it suggests the universe has a beginning. The Big Bang is like the moment the simulation started. The low entropy initial state is like the simulation being initialized. If we're in a simulation, the arrow of time would make sense. The simulation started at some moment in the past, the Big Bang, and is running forward in time toward heat death. Time flows in one direction because that's how the simulation computes, step by step into the future. The increasing entropy might be a feature of the simulation, a way of tracking information loss and computation as the simulation progresses. Quantum tunneling and barrier penetration. What it is: in quantum mechanics, particles can pass through barriers that should be impossible to pass through classically. This is called quantum tunneling. An electron trapped in an atom can tunnel through the walls of the atom and escape, even though it doesn't have enough energy to climb over the barrier. This happens because quantum particles are described by wave functions, and waves can penetrate barriers. The probability of a particle being on the other side of the barrier isn't zero. It's just small. Quantum tunneling is responsible for radioactive decay, certain types of chemical reactions, the sun's fusion reactions. Without tunneling, the sun wouldn't shine. Life wouldn't exist. Quantum tunneling is taught in physics classes, but most people don't realize how fundamental it is to life. Many chemical reactions in cells depend on tunneling. The sun's energy output depends on tunneling. Connection to simulation quantum tunneling is interesting because it shows that particles don't have definite positions and velocities. Instead, they're probabilistic. They're described by probability distributions. In a simulation, particles might not be stored as precise positions. Instead, They might be stored as probability distributions. The simulation would compute the evolution of these distributions. Tunneling would be a natural consequence of representing particles this way. The barrier is just a region of low probability amplitude, but probability waves can leak through. This suggests that the simulation doesn't track exact positions of particles, only probability distributions, which is more computationally efficient than storing precise coordinates for every particle. The vacuum catastrophe. What it is in quantum field theory, every point in space contributes energy to the vacuum. These contributions are enormous. When you add them up, the total energy density of the vacuum should be astronomically large, about 120 orders of magnitude larger than what we actually observe. But we observe a small non-zero vacuum energy, dark energy. It's about 10 to the power of minus 10 joules per cubic meter. This is called the vacuum catastrophe or the cosmological constant problem. Why is the actual vacuum energy so much smaller than the theoretical prediction? Some physicists speculate that there's a deep symmetry that cancels most of the contributions, leaving only a tiny remainder. Others think we're missing something fundamental about quantum field theory. The vacuum catastrophe is obscure because quantum field theory calculations are technical, and the problem is usually discussed only among theoretical physicists. But it's one of the biggest unsolved problems in physics. The fact that our best theory predicts something 120 orders of magnitude wrong is embarrassing. Connection to simulation. The vacuum catastrophe is interesting for simulation theory because it suggests something is wrong with our understanding of quantum field theory. Maybe the problem is that we're thinking about the vacuum wrong. Maybe the vacuum isn't filled with infinite virtual particles. Maybe it's computed differently. In a simulation, the vacuum might be simpler than quantum field theory suggests. It might be represented as just empty space, with particles created on demand when needed. This would avoid the vacuum catastrophe. You don't sum up infinite contributions because you don't compute infinite virtual particles. The small, non-zero vacuum energy we observe might be a computational artifact, the energy cost of maintaining the simulation. Non-commutative geometry, what it is. In ordinary geometry, coordinates commute. If you move right then up, you end up in the same place as if you move up then right. But in non-commutative geometry, coordinates don't commute. The order in which you apply them matters. This might sound abstract, but it has deep implications. Some physicists have proposed that space-time at the Planck scale is non-commutative. Space and time don't quite commute at the most fundamental level. This could explain quantum mechanics. It could resolve infinities in quantum field theory. It might be a step toward quantum gravity. Non-commutative geometry is obscure because it's highly mathematical and speculative. Most physicists work within the framework of commutative geometry, ordinary geometry. Connection to simulation. Non-commutative geometry is interesting for simulation theory because it suggests space-time has a discrete structure. In a simulation running on discrete computers, space-time would naturally be discrete and potentially non-commutative. The non-commutativity might reflect the fact that the simulation computes space and time in a specific order, and the order matters. Or it might reflect deeper structure in how the simulation encodes position and time information. The weirdness of quantum field theory. What it is, quantum field theory, is our most successful theory of physics. It describes particles and forces with extraordinary precision, but it's conceptually bizarre. In QFT, there are no particles. There are only fields. invisible, infinite, permeating all of space. Particles are excitations in these fields. An electron isn't a thing. It's a ripple in the electron field. A photon is a ripple in the electromagnetic field. But here's the weird part. The fields are quantized. They vibrate in discrete units. The minimum energy is never zero. There's always some quantum fluctuation. And when you do calculations in QFT, you encounter infinities. You have to use a technique called renormalization to make the infinities go away. This works, but it feels like a mathematical trick rather than a fundamental understanding. Most physicists accept QFT and use it to make predictions, but many are uncomfortable with the theoretical foundations. Most people don't know about quantum field theory because it's taught only to physics graduate students. But it's fundamental to modern physics. Connection to simulation quantum field theory is relevant to simulation theory for several reasons. Fields as information. Fields might be the simulation's way of storing information. Instead of tracking individual particles, the simulation tracks fields and their fluctuations. Quantization. The fact that fields are quantized, come in discrete units, suggests a discrete substrate. The simulation might have a minimum unit of energy corresponding to the pixel size of spacetime. Renormalization. The need for renormalization to remove infinities might indicate that QFT is an approximation, that we're using the wrong mathematical framework. A discrete simulation wouldn't have infinities. It would have a natural cutoff at the Planck scale. The vacuum. The quantum vacuum with its infinite fluctuations might not be real. In a simulation, the vacuum might be simpler, just empty space, with particles created on demand. The hierarchy problem. What it is, in physics, there's a huge discrepancy between the strength of different forces. Gravity is incredibly weak compared to the other forces. The gravitational force between two electrons is about 10 to the power of 42 times weaker than the electromagnetic force between them. Why? The Planck scale, where gravity becomes as strong as the other forces, is 10 to the power of 19 gigaelectron volts. The electroweak scale, where the weak and electromagnetic forces unify, is 10 to the power of 3 gigaelectron volts. This is a difference of 16 orders of magnitude. Why is there such a gap? This is called the hierarchy problem, and we don't have a good answer. Possible explanations. Supersymmetry, there might be undiscovered particles that explain the hierarchy. This is called supersymmetry. But despite searching, we haven't found evidence for it. Extra dimensions. Gravity might be weak because it leaks into extra dimensions. The other forces are confined to our 4D space, but gravity spreads out into higher dimensions. Anthropic principle. Maybe gravity is weak because if it were stronger, the universe wouldn't be habitable. We observe a weak gravity because only universes with weak gravity allow observers to exist. The hierarchy problem is discussed in physics papers, but isn't well known outside the field. Yet it's one of the deepest unsolved problems in physics. Connection to simulation. The hierarchy problem is interesting for simulation theory because it suggests fine-tuning. The gap between the Planck scale and the electroweak scale seems arbitrary. Why these particular numbers? In a simulation, the answer might be the simulators chose these values. There are parameters in the code. Maybe the hierarchy exists because it's necessary for stable structures, atoms, chemistry, life to exist. It's aesthetically chosen. It's a feature copied from the simulator's universe. Or maybe the hierarchy problem points to something wrong with our understanding. Maybe we're missing a principle that would naturally explain why gravity is so much weaker. The multiverse and Tegmark's mathematical universe. What it is. Max Tegmark, a theoretical cosmologist at MIT, has proposed that our universe is just one member of an infinite multiverse. But more radically, he's proposed that all possible mathematical structures exist as real universes. The idea is, if something is logically consistent and mathematically well defined, then it exists somewhere in the multiverse. This means there are universes with different physical laws, different mathematical structures, different numbers of dimensions. We happen to live in one where the math produces complex structures and consciousness. The mathematical multiverse is obscure because it's so speculative and philosophical. Most physicists focus on testable science. But it's worth considering because it offers an answer to the fine-tuning problem. We observe a universe suitable for life because we're conscious observers, and conscious observers naturally observe universes suitable for life. The anthropic principle. Connection to simulation. The mathematical multiverse is profoundly relevant to simulation theory. If all possible mathematical structures exist as real universes, then the universe we inhabit is, in a sense, a simulation of a mathematical structure. The simulators don't create the universe. They instantiate a mathematical structure that already exists in the Platonic realm of ideas. Alternatively, from the simulator's perspective, they're creating one instance among many. There are countless simulations running in the simulator's universe, each implementing different mathematical structures. This bridges the gap between simulation theory and mathematical Platonism. It suggests that reality is fundamentally mathematical, and what we call physics is just the mathematics of one particular universe. The black hole, information paradox. What it is. When a black hole evaporates through Hawking radiation, where does the information go? Black holes are described by only a few parameters: mass, charge, and angular momentum. So a black hole can be created from infinitely many different states of matter. They all collapse to a black hole with the same parameters. But quantum mechanics says information can't be destroyed. If you throw information into a black hole and the black hole evaporates, what happens to that information? Is it destroyed? That violates quantum mechanics. Does it escape in the Hawking radiation? But the radiation is thermal. It doesn't seem to carry information. This is the black hole information paradox. It's been debated for decades. The information paradox is discussed in advanced theoretical physics, but isn't well known outside the field. Yet it might be the most important unsolved problem in physics because it concerns the very nature of information and reality. Possible resolutions. Information is preserved. The Hawking radiation somehow encodes the information, even though it looks thermal. This is the most mainstream view now. Information is lost. Quantum mechanics is wrong, and information can be destroyed. This is radical, and most physicists reject it. Black holes don't actually evaporate. Maybe something prevents complete evaporation. Information is preserved in the final remnant. Firewall hypothesis. Maybe the event horizon of a black hole is a firewall that destroys in falling information. This resolves the paradox, but introduces new mysteries. Connection to simulation. The black hole information paradox is crucial for simulation theory because it concerns information. In a simulation, all information would be preserved. There would be no way to destroy information. It's written to the simulation's memory. The fact that quantum Mechanics preserves information, as suggested by most solutions to the paradox, suggests that information is fundamental. Reality is information. In a simulation, this makes perfect sense. The simulation is made of information and computation. Nothing is ever truly lost. It's all encoded somewhere. The struggle to resolve the paradox might be because we're thinking about it wrong. We might be overthinking it. In a simulation, the answer would be obvious. Information is preserved because information is all there is. Panpsychism and integrated information theory. What it is. Panpsychism is the philosophical view that consciousness is fundamental to the universe, not just in brains, but everywhere. All matter has some degree of consciousness. Integrated information theory, IIT, is a scientific theory that attempts to quantify consciousness. It measures how much integrated information a system contains. According to IIT, consciousness exists wherever there's integrated information. This could include brains, obviously, simpler animals, computers, if they have enough integrated information, even atoms and particles, if panpsychism is true. Why it's obscure. Most people don't know about panpsychism or IIT because they're fringe ideas in philosophy and neuroscience. Mainstream science treats consciousness as an emergent property of complex brains, but panpsychism has ancient roots and is taken seriously by some philosophers. Connection to simulation, panpsychism is relevant to simulation theory because it suggests consciousness is woven into the fabric of reality. If consciousness is fundamental, then the simulation itself might be conscious. The computation itself might be aware. This raises a disturbing question. Is the simulator's universe conscious? Is the simulation conscious? If integrated information is the measure of consciousness, then any sufficiently complex system, including a simulation, would be conscious. This suggests that ethical considerations might apply not just to conscious beings within the simulation, but to the simulation itself. The hard problem of consciousness. What it is philosophers distinguish between two problems of consciousness. The easy problem, explaining the functions of consciousness, how the brain processes information, makes decisions, learns, etc. This is hard in practice, but seems solvable in principle. The hard problem, explaining why consciousness feels like something. Why is there subjective experience? Why is there what it's like to see red or to feel pain? The hard problem is attributed to philosopher David Chalmers. It asks, given that we understand how the brain processes information, why does that processing feel like anything at all? You could imagine a zombie, a being physically identical to you that behaves exactly like you, but has no conscious experience. Nothing is like anything for the zombie. But if the hard problem has no answer, then consciousness is separate from physical function. This is dualism, the idea that mind and body are different substances. Most neuroscientists avoid the hard problem. They focus on explaining behavior and brain function. But philosophers take it seriously because it might point to something fundamental about reality. Connection to simulation. The hard problem is crucial for simulation theory because it raises a question. Can consciousness be simulated? If consciousness is just information processing, as functionalism suggests, then consciousness could exist in a simulation. A sufficiently advanced simulation would produce conscious beings. But if consciousness requires something beyond information processing, something ineffable and subjective, then consciousness might not be simulable. You could simulate a being that acts conscious but isn't. This is the philosophical zombie problem applied to simulations. The hard problem suggests that consciousness might be fundamental in a way that information processing isn't. If consciousness is fundamental, then the simulators might have to build in consciousness, not just intelligence. This raises ethical questions. If you create a conscious simulation, you might be morally responsible for the suffering of the conscious beings within it. Looking at all these obscure facts and theories, a pattern emerges. The universe is computational. From quantum field theory to quantum mechanics to the holographic principle, everything points to reality being fundamentally computational. Information is fundamental. Entropy, thermodynamics, quantum mechanics, black hole physics, all are deeply about information. Consciousness is mysterious. Quantum measurement, the hard problem, integrated information theory. Consciousness seems woven into the fabric of physics in ways we don't understand. Reality is fine-tuned. The fine structure constant, the hierarchy problem, the matter-antimatter asymmetry. The universe seems precisely calibrated. There are anomalies. The axis of evil, the WMAP cold spot, the proton radius puzzle, the flyby anomaly. The universe has features we don't fully understand. Discrete structure, quantization, Planck scale physics, possibly quantized redshifts. The universe might have a fundamental grain size. Reality is non-local and retrocausal. Entanglement, the delayed choice quantum eraser. Causality and locality aren't what they seem. These observations don't prove we're in a simulation, but they're consistent with it. More importantly, they suggest that the universe is stranger, more computational, and more fundamentally connected than our everyday intuition suggests. Whether or not we're in a simulation, the universe is genuinely bizarre, and that's what makes it worth